Hello, my name is Eric Conway. I am the Senior Vice President of Technology in the Cyber and Engineering sector at BigBear.ai. I want to welcome everybody to day 2 of the AI and Quantum Computing Symposium here at Dreamport in Columbia, Maryland. I am going to introduce to you our first speaker of the day, Dr. Reggie Brothers, who is the Chief Executive Officer at BigBear.ai. He is the Chief Executive Officer here at BigBear.ai, which is a leading provider of artificial intelligence, machine learning, and cloud-based big data analytics, cyber engineering solutions, and more. Dr. Brothers has an extensive expertise in science and technology, business development, and innovative management in public and private sectors. Previously, Dr. Brothers was the Executive Vice President and Chief Technology Officer of Peraton, a leading mission capability integrator and a transformative enterprise IT provider. Prior to that, he was a principal at the Chertoff Group, a leader in security and risk management advisor services, where he developed growth strategies, identified market solutions, and advised clients on evolving threats. In the public sector, Dr. Brothers has served as Undersecretary for Science and Technology at the U.S. Department of Homeland Security from 2014 to 2017, and as the Deputy Assistant Secretary of Defense for Research at the Department of Defense from 2011 to 2014. Dr. Brothers has also held senior roles at BAE Systems, the Defense Advanced Research Project Agency, or DARPA, the Charles Stark Draper Laboratory, Envoy Networks, and the Massachusetts Institute of Technology Lincoln Laboratory. He holds 5 patents and is a distinguished fellow at Georgetown's Center for Security and Emerging Technology, and is a member of the Visiting Committee for Sponsored Research at MIT. So I want to welcome Dr. Brothers to the stage to give the opening remarks for day 2. Thank you.
Eric, thanks so much. We appreciate it.
Thank you.
Thank you. So good morning. And again, welcome to the second day of the conference, the AI and Quantum Symposium. I want to thank UTSA and thank the Matrix for helping to organize this. I think it's a wonderful event. So let me first talk a little bit about Big Bear to give you kind of some context. So our core mission is to improve the ability of humans to make critical decisions. And to do that, we use artificial intelligence to augment the art and the science of human decision-making. Our solutions and products are built around a threefold paradigm, and this threefold paradigm is as follows. 1, we observe the world. We collect data on relevant behaviors across many domains. And then 2, we orient the data. We use machine learning and automation to extract and model the relationships and association found in data. And 3, dominate. We dominate by simulating effects. We generate probable future states and the impact of various course of action, and educate and inform users on the outcomes. We apply our techniques to achieve data-driven decision dominance and apply them to today's most challenging domains. So, for example, space, maritime, cyber, supply chain, healthcare, and more. Customers of ours include the U.S. government, the Department of Defense, commercial organizations that operate on some of the most critical and sensitive networks in the world, performing tasks that protect our national security, economic health, critical infrastructure, and military dominance. The criticality of these missions underscores the importance of creating, maintaining our edge globally when it comes to AI technology. That is continually advancing and improving the state of the art in this technology that is rapidly becoming foundational to maintaining a competitive edge in the world. Let me give you a quote. So Eric Schmidt of Google and Bob Warwick, the former Deputy Secretary of Defense, they both co-chaired the National Security Commission on Artificial Intelligence. In that report, they state that AI is an inspiring technology. It will be the most important tool in generations for the benefit of humanity. However, they acknowledge that America is not prepared to defend or compete in the AI era. Despite exciting experimentation of a few small AI programs, the U.S. government is a long way from being, in quotes, AI ready. So one critical element in competing globally is a close partnership between industry and academic institutions to perform the fundamental research on which tomorrow's AI capabilities will be based. At Big Bear, we partner with a wide variety of academic institutions to support advanced research and development, and to help build the next generation of engineers, data scientists, and cyber and AI experts. So this symposium is a great example of how private industry and academia can come together to foster a collective understanding of the state of the art of technology and identify what remains to be done around topics critical to a nation's success. It was in this context that Big Bear first partnered with UTSA this past spring to discuss the convergence of artificial intelligence and quantum computing. AI, artificial intelligence, and quantum computing are both examples of transformational technology that will alter the world in which we live in tremendous ways. AI has already transformed much of the world in which we live, and we find ourselves in the middle of a new wave of AI technological revolution, one in which we'll see AI transition from statically trained models to what's capable of reasoning, understanding, and forming collaborations with human operators. As we saw here yesterday, there remains much research to be done to realize this vision, to bring AI to the edge, and bring new types of models into operational environments that ensure AI is accurate, it's safe, ethical, reliable, explainable, and continually learns. But today's artificial intelligence operates on classical computers, which have limited computational capabilities that restrict its functionality. Graphical processor units and high-performance computing have enabled recent advancements in capability, but remain limited. AI is likely to require a new paradigm in computing, and quantum computing may be that to achieve significant progress. It is our hypothesis that quantum computing can provide a computational boost to AI, enabling it to tackle more complex problems. So today, day 2 of the symposium, we explore today's current state of quantum computing and then its role in helping to achieve the goals of the next generation of AI capabilities. The morning discussion will focus on establishing where we are today with quantum computing, what we know and what we don't know, and we separate the fact from the fiction with respect to the press releases and claims of quantum advantage growing every day. Our afternoon speakers and panel discussion will focus on the convergence between AI and quantum computing, identifying the advancements in platforms, algorithms, benchmarks, and workforce development required to make quantum backed AI a reality. Following this symposium, we hope to have the following outcomes. 1, form a collective understanding of the state of the art of AI and quantum computing. 2, identify areas where further investment in research and development is required. 3, identify where academic and industry partnerships can help accelerate development. And 4, understand concrete actions we can begin taking today to prepare for quantum advantage and its impact on AI technology. So thanks again for everyone who came together to address this important topic. And we look forward to collaborating with you much more in the future. So thank you very much. Enjoy the day. Welcome back. So I'd like to introduce our keynote speaker, Dr. Michael J Hayduck, who is the Deputy Director of the Information Directorate of the Air Force Research Laboratory in Rome, New York. The director's mission is to lead the development and integration of Air Force warfighting information technologies, command, control, communications, computers, intelligence, and cyber. Dr. Hayduck plays a key role in overseeing an annual budget over $1.6 billion, leading the activities of over 1,200 employees. Upon completion of his graduate studies, he served as a research engineer where he developed ultra-fast solid-state pulse lasers for optical communication systems. He became the acting chief of the electro-optic components branch, in which he led the development of components and subsystems for advanced radio frequency and electro-optic Air Force sensor systems. He then became the chief of the emerging computing technology branch, leading fundamental exploratory research and development in nanocomputing, quantum computing, and optical computing for advanced computing architectures. From 2011 to 2019, on the role of chief of the Computing and Communications Division, led the discovery, development, and integration of affordable computing, networking, and communications technologies. With over 50 journal and conference papers published and 1 U.S. patent, Dr. Hayduck is responsible for coordinating the entire quantum information science research portfolio of Air Force Research Laboratories. So thank you for being here, and please welcome Dr. Michael Hayduck.
Thank you very much, and thank you, Dr. Brothers, for that great introduction. It's a pleasure to see you again. I know our paths have crossed in the past, so it's just a huge honor to be here today. I really want to thank the conference organizers, not only certainly for the invite, but really for putting together a conference and this very unique topic that I think is just going to be of paramount importance as we go forward. So I know we're trying to push the slides right now, waiting for them to come up, and we'll be ready to roll. And there we go. So thank you again for the invite. My talk today will be focusing on advanced computing technologies at the Afrl Information Directorate. So what I'm going to look to do in the next 45 minutes or so is really show you some of the different technologies we're working on, not only in machine learning and quantum computing, but really a lot of our hardware work that fits together. And Dr. Brothers had alluded to that in terms of transformative technologies and being able to bring AI to the edge. So that's, directly in line of our goals here in Rome in the Afrl Directorate. So next slide for a brief introduction. So what we'll be talking about today, I know folks probably aren't too familiar with Afrl or specifically the Afrl Information Directorate. So I'm just going to spend a couple minutes really familiarizing everyone on some of the things we do here in Rome. I'm going to begin with a discussion on quantum information science. You'll notice, I'm going to be a little more broad than just quantum computing. And there's a reason for that. One, the technologies we're developing really do all play together and really do have an impact. So do some time quickly on some of our quantum work and then focusing on our algorithm work as well. Then I'll turn our attention to some of our nano computing work, including neuromorphic computing, really the hardware basis. And we have a couple things there, both in terms of analog type computing using Memristors as well as CMOS development, teaming with some commercial partners out there. And then finally, I'll conclude with a look at, how do we bring some of these technologies together? And this is a really fascinating program that's just concluded after a 3-year run here at the lab called Streamline Machine Learning. What it's really doing is developing an end-to-end machine learning ecosystem that's open source to get machine learning capabilities out to the field faster and in terms of more rapid updates as well at a lower cost. And we'll get into some really good details on that later on. So next slide. So I couldn't be here today without the Afrl team. So you see several members listed there. Thanks to all of them working in different technology areas. I won't go through each of their names, but they do represent those areas. As Dr. Brothers introduced me, I am the deputy director here. So unfortunately, I'm not the one doing the work anymore, but it's these great folks who are out in the lab doing all this work that you're going to see represented today. But it is a huge honor to represent all of them. And please, I have these names up there also for a reason, so that if you want to follow up on any specific areas, please let me know and we'll be happy to point you in the appropriate direction. So next slide, I'm going to talk a little bit about what we do in the Afrl Information Directorate in terms of our mission and vision. So we're one of 9 technology directorates across Afrl. There's also 9 different geographic locations for Afrl. Specifically, we are located in Rome, New York, upstate New York, really central New York, center of the state. And if there's one thing I'll leave you with when you think of Rome, and you think of the information technologies, it's Rome equals C4I and cyber. And those who may not be familiar with the C4I notation in military lingo, it's command control, communications, computers, I is for intelligence, and of course, cyber. Now we call out cyber a little separately is because it really shows the huge focus that we have on cyber in Rome is really being able to support not only the Air Force, but now our new partners in the US Space Force. So our mission, as it says above, explore, prototype, and demonstrate high impact, game-changing technologies that enable the Air Force and the nation to maintain its superior technical advantage. And again, the Department of the Air Force consists of both the Air Force as well as the Space Force now. And you'll see, a lot of these technologies are relevant to both air and space. Next slide, a little bit about our facilities in Rome. I won't spend too much time on this. I could spend all day talking about some of the great things we have in Rome, but our main campus consists of 30 laboratories and facilities really spread across that C4I and cyberspace. 2 offsites, Stockbridge and Newport, where we do a lot of our field testing, if you will. Newport is our large airframe testing for antenna pattern measurements, far field measurements. Stockbridge, we do some really neat field work there in what we call a controllable contested environments. You can see some of the technologies that we list there. It's a 300-acre site that includes UAS capabilities, networking capabilities, and then really be able to link the information back about 18 miles to our Rome site for further processing. So as we develop things in the lab and great technologies in the lab, our site is always, of course, transition and getting it out to the warfighter, but we need to do some prototyping and some field tests. So Stockbridge and Newport allow us to do that. One other thing to point out, I didn't want to, spend a lot of time on it, is that we have what we're calling an extreme computing facility standing up. New facility. We've just been very fortunate to have the Air Force put $5 million of funding into this new facility. And this is really it is very relevant to what we're talking about today, because it's bringing together things like quantum, artificial intelligence, machine learning, neuromorphic computing, and nano computing as well, all in one facility. So obviously separate technologies being worked, ultimately with lots of integration and touch points between them, but really great capabilities and state-of-the-art environmental control for all that. So more to come on that in the future. Of course, inviting folks, as always, to come out and visit us. Last one on our facilities would be our Innavari Advancement Center. I know some folks have heard about this. We've gained a lot of traction with this. This was stood up just last year in 2020. It's located just outside our security perimeter here in Rome, New York. And what this is, it's our open and collaborative ecosystem. It's our open campus, if you will, where we're really pushing the limits on foundational technologies. You'll see them listed down there. UAS testing, quantum, neuromorphic, nano computing, all the technologies we're talking about here today really fit into that. Why did we develop this facility? Well, it's really a partnership between New York State, the county we sit in, Oneida County, the city we are in, Rome, New York, as well as some of our other key strategic partners. And this really allows us to partner with non-traditional folks who may not be able to easily work with the Air Force, just because, they may be international citizens. They may, not have cost accounting systems in line with the Air Force because they're startups. But that doesn't mean, they're not performing valuable work. So this allows us to access those folks and really to work side by side with them. And we have laboratories set up there as well, state-of-the-art quantum labs, as well as nano labs as well. So there's gonna be a lot more to come on that in the future, but if you're interested in learning more about it, please let me know. Next slide. All right, here we're gonna start getting into the meat of the talk, if you will. The first section we're going to go into is quantum information science at Afrl. As Dr. Brothers mentioned in my introduction, I'm very fortunate, as well as being the deputy directors, to coordinate quantum research across all of Afrl. We really bin the research into 4 main areas that we'll talk a little bit more as we go through this talk. That's timing, sensing, communications, and networking, and computing. And you'll see kind of where the work is being performed at the Afrl sites within the US. And then also 3 sites, international sites that Afrl has: London, Tokyo, Santiago, Chile. And in fact, we're actually setting up sites in Brazil as well as Australia, just getting going. But you'll see in the bottom, I won't go through the 2-letter acronyms. Those are our technology directorates, but you can see the different areas and some of the POCs that are working those different areas. We're not going to spend time today going into those areas other than on the next slide, which we'll flip to now. And here, this is really the why question, right? Why is the Air Force interested in quantum information science as a whole? And it may seem, pretty intuitive to folks, why we're interested in quantum computing, but there's all these other technologies that I talked about, and you can see them kind of color-coded, such as timing, sensing, communications, networking, and computing. Just to spend a little time on that. So of course, with clocks, we're very interested in stable clocks, longer term stability, being able to shrink them down in size so that we can put them in space to synchronize platforms. And the sensing piece of it, long duration unaided inertial navigations in times of, say, losing GPS signals that we are so dependent upon in all of our lives, whether military or civilian. So how can we use quantum sensors to take advantage of that? Things like magnetometers, inertial sensors, accelerometers, fiber optic gyros, all those kind of things fit together, as well as in an architecture that brings them all together. And then on the communication side, really we term this networking, and this is entanglement distribution, going way past QKD. So really focusing in on entanglement distribution. An obvious application for us would be low probability of intercept communications, and certainly being able to tie networks together and really tie sensors together, possibly distributed quantum computing together, but it's really how we get to the network. And then finally, computing. And I'll talk about this later on, but what we're really interested in are algorithm and problem-based development. We're not developing per se the hardware at AFRL for that, but we're really leveraging what the commercial industry is doing. And you can certainly see, things that will be of interest to there would be things like quantum simulation, enhanced machine learning, as well as optimization type problems. So overall, our large AFRL program. Next slide. Here we're going to go into a little bit of the technologies, and I'm not going to go too deep on this. You might be wondering, why I'm going into this in this type of talk, but really it just shows, the different technologies, how they all feed a computing architecture. And really what we're focusing on enrollment network architecture, but really distributed processors are one of the things we're involved with as well along the network. So developing the different pieces of the network, as we like to say, how can we build the network faster, quantum network faster? You'll see one of the main drivers for us are photonic-based qubits. And this is really bringing together integrated photonics. You can see the advantages listed. It's really the long distance carrier of quantum information is why we're pushing on photonics. Lower left-hand corner, you see a 300 millimeter quantum wafer, something we're incredibly proud of. This is has been designed by us in-house, fabricated at the AIM Photonics Institute, which is the DoD's manufacturing institute for integrated photonics. Really allowed us to take things from the lab and get them onto chips and really make things much more practical. You'll see things in the middle, such as ultra wide bandgap photonic platform. This is our silicon nitride work, makes the wavelengths compatible with what comes out of our ion traps, and especially ytterbium wavelengths. Upper right corner, this is an entangled photon source for spontaneous 4-wave mixing. And then finally, some work that we've done with the Rochester Institute of Technology, a really key partner for us on large arrays of Mach-Zehnder interferometers. So you can see this kind of opens up, once we're able to integrate things and package things, how we can really start moving from 4x8 optical tables out into, the field. Next slide is on superconducting qubits. This is a new area for us, relatively new area for us in AFRL. We're really proud to stand this up, being led by Dr. Matt LaHaye. And here we're talking about superconducting films and how you can take billions of electrons that once you move them to a cryo temperature, these then move into a single quantum state. So you can see how that could be very useful. Certainly very interested in working with the commercial players out there. In fact, we have partnerships with many of them. IBM, Rigetti, and Google are certainly leaders in the field, and we're pleased to work with a few of those large partners out there. You can really see, how you get the key information here, and it's really the fact that this is the processing piece. So no surprise when you think of quantum computers, that superconductors play a lead role in that. And the real reason is that once you get to those cryo temperatures, the circuits behave like an atom with very discrete energy levels. And this also, the key part of superconductors and their scalability is that it allows us to integrate with the other technologies quite easily as well. Next slide. Real key technology for us being worked by Dr. Kathy Ann Soderberg is our trapped ion qubits. This is really the memory. You can't have a network without memory. And really, if you think about distributing quantum computers, of course, you're going to need memory. So trapped ions are one capability for that. We've kind of focused in on ytterbium-171. Several years ago, we were the first DoD lab to actually trap an ion using ytterbium. We're now looking at, a more unique material system, barium-133. Moves us to different wavelengths that would make us a little more compatible and more efficient with the integrated photonics that I showed on previous slides. But really, the advantages there, you can see not only long-lived memory, but provides identical qubits, so scaling. Again, another reason why this is of such high interest to the commercial quantum computing world. You've probably seen in the news IonQ, who's just gone public and just going, just making great technical progress with their scaling that's out there. I think we have enough there. Oh, and we'll just stay there for a second. Upper right side, really cool thing that we're working on is how to use a single fiber to both be able to manipulate and read out the trapped ions, because we're operating at different wavelengths. We're able to separate those out. So again, getting towards more compact things and getting out of 4x8 optical tables, off of 4x8 optical tables and out into the field. Again, key part for us is on the next slide is how we bring all these things together. So this is really our heterogeneous qubit integration, bringing together those different pieces. So to reiterate, the work being led by Dr. Mike Fanto and photonics is really the transport piece of it. The superconducting piece is the fast information processing, and the memory is provided by the ion. So bringing everything together, especially with transduction techniques, are an active area of research for us right now. Next slide. So once we start integrating things, what do we do with them? So this is really our vision, and I really thank our team and Dr. Soderberg for putting together this vision. So you can see kind of the different colors there with basic, applied, and advanced research. So the basic research is at the Innavari Advancement Center, where we're really looking at foundational research capabilities. We can then move those into our in-house laboratories. I talked about our new extreme computing facility. And then finally, how do we take these out to our test sites, and that being Newport and Stockbridge? And not only just the quantum network, what do you do with a quantum network? Well, we talked about distributed computing, being able to tie together clocks and sensors. So we see this as a really nice capability for us, not only within the Air Force, but DoD-wide, as well as with our industrial and academic partners as well. All right, next slide. Certainly of key interest is our quantum algorithms and software development. So just to spend a few minutes on this, I talked early on how we're really working on developing hardware more for things like the quantum network, how we develop the network faster, if you will. But where do we go with algorithms and problem space development since we're not developing hardware? Well, what we're really doing is partnering with key players out there. So you see on the lower left, this partnership that we entered into 2 years ago with IBM. We became a hub on a Q network, the first DoD hub on that, and the only one right now. Right now we have, I believe, it's growing every day, so don't quote me on this one, but it's about 12 partners right now spread out amongst DoD, Navy is a key partner for us, national labs, some industrial partners, as well as many academic partners as well, all really solving problems that are of interest, not only to the community as a whole, but really specifically of interest to the Air Force. And this allows us cloud-based access to the latest IBM hardware. It's been a great partnership for us. Important thing to point out there is, of course, it's not the only platform that we're interested in. We're looking at other platforms as well, other types of technologies in the NISC area, noisy intermediate scale quantum computers. So certainly as the technologies evolve, we'll be looking at the different platforms as well, and really what scales the best when what fits our problem spaces the most. You'll see a list of publications there as well from our team. Really proud of this, that we're really, not only teaming with the right people out there, but really able to lead some of this research, and especially focusing in on which is going to be relevant to the Air Force as well. In fact, we'll probably be, just a little hint, upcoming Q2B conference, we'll be talking a little bit more about our in-house work in this area. All right, so now, as I promised, we're going to shift gears a little bit and move towards our neuromorphic computing area, as well as our nano electronics work. I know some folks in the audience are familiar with this. And this is really, how do we get edge computing? How do we push AI out to the edge? So you can think about the Air Force, certainly, and things that we're interested in. We take in large amounts of sensor data. I know this was talked about yesterday in some of the panel sessions. Well, what do we do with that data, right? We traditionally, we can take it, use large pipes, if you will, high bandwidth communication systems, ship it down to the ground for further analysis. Well, a lot of that data never even gets looked at because there's so much there. But what happens if we can process at the edge, maybe cue some sensors for a tighter look, and really process and come up with a decision advantage to the warfighter? So we really believe that, to get there, things like neuromorphic computing are going to allow us to do that. What is neuromorphic computing? For those who may not know, it's brain-inspired, low swap computing for really putting AI and machine learning out to the edge. We'll do a comparison here. I really like this chart, and I thank Dr. Ching Wu for putting it together. It's just an awesome representation of comparisons between a von Neumann computer, which are traditional CPUs, as well as the further out computer, really state-of-the-art neuromorphic type computer. So you see in von Neumann computer, really good for precision, high speeds, of course, synchronous, binary encoding, which makes it very power high in power consumption. Memory computation bottleneck. We'll talk a little bit about that later on when we get to memristors, the difference there. And of course, it needs explicit programming for function. Now you look at the parallel over there, which is a neuromorphic computer. So really focuses in on learning and inference, operates at low speeds. It's asynchronous. It's low precision, but yet very reliable, uses spike encoding, which is very energy efficient. You can certainly have large connectivity when you think of a brain-inspired architecture. And now a really key thing, unified memory and computation, really bringing how you compute within memory to the table, and allows you to have learning from data and environment. So there's three pieces to this and three focus areas of our program listed below. So the first piece is our hardware piece, neuromorphic processor, really the computing architecture. And I think of this as more of our really CMOS type architecture. So shown there is our work with the IBM True North processor. We're also working with Intel on the low E-heat processor. The middle piece of it is our nano electronics, and this is really how you move towards different materials that may give you an advantage, may make a computer more like the human brain, really taking advantage of that. So these are memristors, which function as artificial neurons and synapses, and we're going to go into more detail on that as we go later on. Now, what do you put on top of this to be able to actually use the hardware? Certainly our models and algorithms of machine learning. So all these pieces tying together, really providing a really huge advantage in computing architectures. Next slide. So this is, again, a really neat slide put together by Dr. Joe Van Nostrand, kind of showing, if you will, the quick history of electronic computing and where we are today. Certainly, starting out with the transistor well over 60 years ago now, moving to the IC processors and finally cloud-based AI. But we've hit limits, of course, along the way, not only in classical architectures, but certainly in FPGAs as well. So you can certainly see highlighted there, uncertain future of scaling, defect intolerant, you hit the bottlenecks and von Neumann architectures. How do we get past this? And that's really going to be the focus of the next several slides as well. And really moving towards the biologically competitive intelligence as our overall vision. Next, here we go into just kind of a quick overview and tutorial, if you will, on memristors or memory resistors. And you can see a lot of kind of information portrayed on this slide. But what I really like to always talk about memristors is being the magical missing fourth circuit element, first postulated in 1971 by Professor Leon Chua, confirmed in 2008 by first by HP group by Dr. Stan Williams. Really took off after that, and Afrl and our in-house team here in Rome really jumped in right around that same time as well. Once we said, maybe we could start forming computing architectures around these very interesting circuits as well as devices. And what a memristor really does is it relates charge and magnetic flux together. It's a two-terminal device. And it really is, I think what it comes down to mostly is resistance is a function of the history of the voltage applied across it. And that gives it some very unique properties. And a key part of all of this is size, weight, and power. And this is what is really driving, how we can get down to low swap. And why is that important? So certainly for the Air Force, especially as we move towards edge computing and AI at the edge, it really shows, can we put things in UAVs? Can we put things in pods like we've shown here at the lab? We need that low power because platforms are always limited by the amount of power. So that's something that's been a key driver for us as well, is that swap ratio. Next slide goes into a little more in-depth analysis of how we can take the brain type of architecture and move it into electronics. Easier said than done, but why we want to do that, it's really again relating how we can have neurons and synapses replicated in electronics, whether traditional CMOS or CMOS combined with memristors. You can certainly see some of the connections there, if you will, and really all driving towards swap efficient nanoelectronic AI hardware. Some of the key things to point out on the slide is there is a lot of information you'll see that to implement in CMOS, such as with the True North or Low-He processor, one synapse requires approximately 50 transistors, as well as multiple passive elements. And one neuron takes 10 to the 6 transistors. Now, if we can do this in nano components, such as a Memristor, you can see things like one synapse, it can be formed by one Memristor, one neuron can be formed by 2 Memristors. So really, again, lots of savings there, lots of challenges with fabricating Memristors, but certainly a lot of progress has been made since the 2008 really demonstration of Memristors. We're very proud to be a part of that as well here at Afrl. All right, next slide just shows how it can be done. 2 real main ways. One is with synapses, you design the desired hysteresis. You can see the current as a function of applied voltage. And this is memory, really functioning as memory with plasticity. You can see the different types of metal oxides there, if you will, forming memristors. And then there's the Axon type, which is really more of the threshold type, the integrate and fire, where spikes that are generated. And burst modes can also be used, and this really provides a different type of functioning. So all very valuable, all things that are being worked on in the field. And I think one common question is always, and you see them listed there, is what types of memristors are out there. There's many different types, and we'll get into this a little later on. A lot of it is being driven, of course, can you introduce it into a CMOS processing line, and can you integrate it within the line, whether it's hybrid, front end of the line or back end of the line integration. So different types of memristors are metal oxides, chalcogenides, and amorphous silicon, many of which we've worked on here at Rome. Now, turning our attention to a new program, and I thought this would be of interest to the audience. This program is a tri-service program, so that between Army Research Lab, Naval Research Lab, and Air Force Research Lab. And this is what we call our neuropipe effort, a neuromorphic hardware development. And this is a 3-year program just kicking off. And it's really looking at not only how we can take improvements in very basic materials research, devices research, fold it into an architecture, fold it into something that can be large scale integrated, and then ultimately taken out to provide some capability, some really, we're not going to get there right away, but ideally, how we can get towards not only the processing towards the edge, but really more along the lines of being able to deploy artificial intelligence type capabilities. The ARAP proposal, this is, I should mention, ARAP is Applied Research for the Advancement of Science and Technology Priorities. It's funded at the Office of the Secretary of Defense level. They're typically 3-year programs with pretty large amounts of funding attached to it. So we do have a large framework of collaborators on this program. You can see some of the words here that I won't spend a whole lot of time on in the interest of time, but we're really pushing at developing these new capabilities all the way from the materials, devices, the architectures, as well as bringing in the software to really target, an application. And you see that listed in the kind of the diagram before. State-of-the-art CMOS combined with these new components, which we're really targeting here, memristors, looking at how we integrate those and then really deploying this into a platform there, an autonomous type of platform, which we'll talk a little bit more later on. But in terms of payoff, so certainly not only increasing and speeding up the development, accelerating the development of neuromorphic computing applications and pushing AI out to the edge, does get us to things such as 100x reduction in consumed energy for processing. So again, very important for those small types of platforms that you see there, which is an Army platform, but really also moving towards things like 3D navigation, target classification, C2, et cetera, that can be done with these types of platforms as well. The technology gaps are shown on the next slide. Won't spend a whole lot of time here on these, but really, because we've talked about these, but this is, again, how we can take this into what's called a throwbot. This, in this case, being a naval research platform, which is being developed in their lab for autonomous systems research, the laser lab, and really would like to have, on-chip learning rather than being able to train off-chip. How can we do it on-chip? And being independent of the cloud, which you might imagine, in times of conflict, you might be cut off from the cloud. So if you have those capabilities on platform, it'll be much easier to get around. And then you can see certainly, why are we moving towards this? So certainly, and we'll talk a little bit about this later on when we get towards the CMOS type capabilities, but things like True North, Loihi, based on current state-of-the-art CMOS technology out there. But from the DoD's perspective, and you'll see this in several slides, really, we need great platforms that are out there right now, but we certainly need to move past that and get to something that can really improve not only performance, but size, weight, power as well. Next slide, we just have a couple more on this topic. In the interest of time, I'll keep moving here, but this really just brings together and shows at the bottom, you can read through this, where we're starting out with, post-packaging integration. So they have the most flexibility there with different diverse material systems. Where we're going towards is back of end of the line integration. We've already done some work here at Afrl in that with our partners at College of Nanoscale Science and Engineering at SUNY Poly in Albany, New York. And then finally, how do we get towards, full, say 12-inch wafers in full scale integration? Here, of course, you're going to have limited fab capability materials. So you're going to be certainly limited with what you can do there. So we really have to kind of think ahead as to how we're going to develop a very exquisite material system, and can they be something that can be easily put into the production line. Next slide just kind of shows the vision as well. So there's going to be a lot more results that I'll be able to show next time when we meet, but really, again, showing AFRL piece, it's kind of developing that front end of the line CMOS control chip. The Navy is bringing together their materials and device research, and the Army is bringing together the prototype platform testing, as well as the on-chip learning and really the software piece of it. So certainly hardware is not any good unless you're able to use it in specific applications. So we really thank the Army for all of that. All right, now we're going to move back towards two more sections here in about the next 15 minutes or so. Here I'm going to talk about the work we've done with IBM and the True North processor. You can see a great timeline spread out there. This started out in 2008. So, no surprise, right around the time that memristors were first demonstrated, neuromorphic processing became of high interest to DARPA, and the Synapse program was stood up. We were a part of that program in terms of being able to contractually look at some of the different technologies being developed. But what I really like to point to is in 2014, we were the first lab outside of IBM that actually took in a Synapse processor to do some hands-on evaluation and application development for it. And I can tell you it's been a great partnership ever since then. It's led to many generations and many iterations of what the True North processor was. So if you look at the NS1E that we used in 2015, the 1E references 1 million neurons, as well as 256 million synapses. We then took that and put it into 16 boards in the next slide, next piece of it in 2015, which of course translates directly to 16 million neurons and 4 billion synapses. And then finally, we built this into a cluster type platform where we took 4 pieces of that system, where we were able to demonstrate SAR or synthetic aperture radar capabilities, as well as target detection and classification with some other customers. So you can see some of the timelines there, really proven to us within the Air Force, as well as the DoD, on how we could take these things and really bring them out into the field. So some of our research capabilities, this is our vision. So you can start out with the near term. So Agile Condor, really hybrid type platforms. So things like GPUs, CPUs, as well as neuromorphic processors, all combining, putting into a pod. We've done some great demonstrations with this. Unfortunately, I'm not able to show some of the data there in this open environment, but we've been really happy with what we've been able to show, how we can take processing and put it out at the edge. You can see some of our initial demonstrations, and I'll have more on this later on, but 10x power reduction, 20x throughput increase using the initial versions of the True North. Midterm, certainly we're looking, and this is really where we're at right now, is how we can fold memristors into these types of things, as well as developing the next generation of the true north, known as the North Pole. And the Cheetah chip is of interest because that is something we're developing in-house at AFRL, more along the lines of a traditional CMOS type processor for our requirements here within the Air Force. And then far term, again, where we can really tie in memristors, not just develop the memristors, but integrate them with CMOS as well. And then really developing both neurons and synapses that would drive that. So results. So SAR target recognition, again, synthetic aperture radar. You'll see comparisons between the NVIDIA Jetson board, which is the top data, as well as the lower boxes, which is the IBM NS1E. And you'll see the comparisons there in terms of 20 to 30x energy consumption decrease at the same classification accuracy. And really, how did we get the different classification accuracies? But that was really driven by the model size and how we could increase the model size to get to that data. Next slide. This we were already talked about, but just to hit upon it again, this was done a few years ago now, but really put the stake in the ground for what AFRL is doing in neuromorphic processing using the true north. Only things really to point out here is the comparison between GPU, the NVIDIA processor. You see a 10x reduction in power, as well as a 20x increase in throughput at the same accuracy. So again, really powerful initial demo that we built on for some of our other work as well. So our next slide here is anomaly detection with spiking interference. So this is showing some of the capabilities that have been demonstrated recently. And this is really how we implement Kajin confabulation algorithm for that anomaly detection. And specifically here, you'll see in table 4.3 is a 20 to 30x increase of energy efficiency over GPUs. And then when we compare them to CPUs, 1000x increase of energy efficiency. So very powerful capabilities there. But we can't stop there, and we realize that we're not solving all the problems. So we have lots of rooms for improvement. I talked about how we're moving towards the next generation of the true north processor known as the North Pole. Really neat thermal image is shown on the upper right-hand side, and you can see where the hot spots are, which means where it's consuming a lot of power. So your Ethernet port there, as well as your FPGA. And the FPGA is the key piece in converting the data to spikes. So, those were certainly seen as areas that need to be improved on. So how we get there are shown not only in the limitations, but the leap forward that is there. So currently being worked on and fabricated. So we'll hopefully have some early data very soon that the true north will have. The next slide, I think we're just going to go through briefly, but really, again, memristors and key parts of it. What I really like to focus in on here, digital CMOS versus memristors. Computing architectures certainly right now are limited in von Neumann, and that really being how you have to move out of memory to have compute and to be able to move back and forth. So it really involves a lot of inefficiency there. As you move towards memristors, not only do you get that significant power savings, but you're able to really compute in memory, which of course does drive the power savings as well. So just really, again, highlighting the advantages of memristors. Next slide. Initial comparisons. So this is work that was done with partners out at UMass. UMass, actually some of the early researchers in memristor development from their previous careers. Here I'd like to point out, now as we integrate memristors with CMOS, how does that compare actually to a true north type of architecture? So you'll see some of the data there, and I think this is really neat to show for a 2-layer neural network and some of the capabilities, but really focusing on the data for an increase in speed between true north array versus what we can do with memristor integrated with CMOS, and then energy efficiency, the improvements in that as well at the same classification accuracy. So certainly classification accuracies are key to us. And so it's not just swap, but it's also having the same performance parameters. Some of the work here is the learning algorithm on a crossbar array. You can see some of the data shown there. I think in the interest of time, we'll move on to the next one, which is really our demonstration of an artificial synapse using Memristor circuitry. So two types of demonstrations are shown here. So short-term plasticity. This is really for memory type of development. And then piece two is the long-term plasticity, as well as the learning process. And this really, as you'll see there, really does drive the learning process as well. So two different applications, but really getting towards, how you can take Memristor type circuits, not only develop neurons, but synapses as well. And again, really trying to get towards replicating the human brain. So in the last few minutes here, I'm going to focus in on the machine learning piece and what's called our Streamlined machine learning program. A lot of this, again, I really have to thank our key researchers on this, Dr. Ed Vorenich, as well as Dr. Lee Seversky. You may have noticed some recent demonstrations, actually hot off the press, that just happened earlier this week. So there's a press release out on it showing a collaboration that occurred in this area. And I'll talk a little bit more about that later on, but demonstration between the United States here at Afrl, as well as UK at the DSTL lab using a Streamlined machine learning program. So you see on this slide here, this just kind of summarizes, certainly not all the pieces and partners that are out there and vendors that are out there, but really the machine learning landscape. You'll see certainly commercial, academia, and industry, a DoD piece there as well. It's very diverse, it's very fragmented, many different algorithms and models being developed. So when we look at it from the DoD perspective, how best do we take advantage of all the great commercial work that's being done out there? And really, how do we develop an open framework for that? So on the next slide, really showing what we're trying to get at. So on the left side is, what if the Air Force and the DoD could, and we can go through all of these, but, being able to look at the available algorithms and platforms from sources across academia, industry, and government, and then being able to apply all of that to Air Force, DoD, and applications, while very key here, driving down the incremental cost of algorithm selection, evaluation, and deployment to a near zero cost. And this was really what we're doing. So not only driving performance, but driving cost down, as well as time to development down. And that's shown then again on the right side, what I just stated, certainly how to establish an open DoD ecosystem to maximize sharing and reuse, transparent evaluation of algorithms and models. So the bang box on the bottom, if you could just go back for a second there, is really how we address those challenges to realize this vision and develop an ecosystem to realize that. So in 3 short years, we've made huge progress towards that. Next few slides will really not only show what we have, but what we're doing there and how we can build on certain things. So the government ecosystem here. So what is Streamlined machine learning? This really gets at it. It's an end-to-end ecosystem for rapid, low-cost implementation, evaluation, and deployment of state-of-the-art capabilities for the Air Force as well as the DoD. 3 key tenets here that I'd like us to focus in on it. So maximizes government choice. We get to the best machine learning technology regardless of the vendor. We have the acquisition piece of it, very important to us in terms of how we're able to not only get to the workforce and the talent, but how do we implement and onboard new machine learning algorithms. So you can see some of the results there. And I think I have another slide of that later on, but took 2 weeks to develop the whole pipeline, and then 12K per algorithm. So huge improvement there in terms of being able to bring that on board. So it's not just developing something that's out there, but how we can actually feed it into our cycle as well. And then finally, evaluation and reuse. And it gets to what I just said, it's not just one and done with these models and these algorithms, but how can we then take new data, retrain the models, and add it to the ecosystem so that we can bring new capabilities on board. So it's not just reinventing the wheel as well. So very key to us, which of course would drive the speed as well as the cost to develop it as well. And you see kind of the funnel slide over on the right and all the pieces that feed into it. Next. So what makes a machine learning ecosystem? So certainly if we start out at the top, if you will, item 1, but really if we go around the slide and really going towards the streamlined machine learning ecosystem in terms of what it's all about. And so we'll talk about the different pieces that feed it now. So our community, so not only the contributors, developers, and other stakeholders, but certainly, us as the government, as the DoD, being able to have a repository where we can store things, have metadata, certainly the parameters, performance data, the runtime, of course, is key to this as well. The technology and algorithms. So of course, things are moving very, very fast in this field. So we want access to open source models, as well as the technology. Tools are key to this as well. And obviously allow us to certainly move faster, keep those artifacts, develop and evaluate the models, and then really bringing this together in a development operations or DevOps type of platform development system. And why we would do that is certainly reducing the cycle time of development. Getting into a little more depth here is really, what is our ecosystem architecture look like? So a pretty complicated slide there, but I think we can boil this down into a few key tenets here. So first thing is it's really built on the best of commercial tooling, and you can see how it's the things that feed into it there as well. And then two, streamlined machine learning uses industry standards, open source technology, being able to modularize the platform components, the different components that are part of it. And that really leads to a common standard for maximum flexibility. So you always hear open source within the government and getting away from vendor lock. And that's the third key component of this, is avoiding vendor lock while encouraging the maximum participation from the ecosystem, which consists of stakeholders and platforms. So the next slide. And I'm running a little short on time here, so I only have a couple more slides here before we hit the summary. But this really makes let's see, right here is the key feature of machine learning acquisition for the government. So certainly DoD relevant state-of-the-art algorithms are developed by the global machine learning community. And how do we onboard and take this in? We've talked a lot of this, but really the big idea here is certainly not only the work that's out there, but certainly being able to pull in the right talent for this. Obviously, as the government, we're not able to develop everything ourselves. So being able to access and leverage all that's out there as part of the ecosystem is very key for this. Certainly, pulling in the algorithm is very important. And then being able to use the public model integration software kit, which we talked about before. The results are shown here on the right. This was taken as a pilot back as the program started early on. FY19. You can see some of the data that went into this, but what we really ended up with, average time to implementation was 9 days, start to finish, and average cost was only $12,000. So very low cost of entry there for us. And not only is it one and done, but it's a reusable type of implementation and architecture as well. Next. So finally here, just wrapping up the streamlined piece of it, you'll see kind of the different parts and pieces to this, but it really allows the DoD to go after that much larger pool of developers, researchers, academia, and industry. And not only is it for our benefit, but it really allows us to bring in those partners. I talked about early on, kind of the different business model we have at Afrl and developing things like the Innavari Advancement Center, but this fits all right into it. So it's pulling in those different partners, maybe small startups, maybe those not normally engaging with the government that could be due to the high cost of entry, but being able to bring them in and to be part of our ecosystem in the machine learning area. So that's going to be very promising for us and important for us as we go forward. And I did talk about a little bit already, so I kind of stole my own thunder, but the UK and US, Afrl and DSTL did a demonstration this week, and really what we're looking to get towards, and this was just the first step in a multi-year program, but ultimately the goal is to explore for commanders, from a commander's perspective, how they can have these information in front of them and be able to explore, understand, select machine learning models that they can deploy for certain requirements. And of course, being able to do that on the fly is going to be something very important as we go forward. So with that, I'm going to pretty much wrap up right now. So in summary, we've talked about the different pieces that go into really what we call our extreme computing platform here at AFRL. And first and foremost, we talked about quantum information science technology, the different parts of it, really focusing in on networking hardware, which can be leveraged for computing hardware as well. Certainly as we build the network, those different types of technologies, be it superconductors, ion traps, or photonics, are all key and all very important to us. We're very proud of the fact that we're working on those 3 qubit technologies here in-house. And I didn't mention it, but certainly if you're interested in learning more about that and possibly partnering with us on some of that work at Innavari, please reach out to me. Then on the algorithms piece of it, we're not developing the computing hardware, the large iron per se, leaving that to industry, but really the optimization, enhanced machine learning, and quantum simulation are the 3 algorithms that are key for us right now that we're really focusing in on. In the NISC area, and certainly as we move forward towards realizing more practical and practicable error-corrected quantum computing systems. And then we talked and spent a lot of time, really the bulk of the talk, talking about non-von Neumann architectures for low-slop applications from both a nanocomputing perspective, using very novel components such as memristors, and then how we apply these in neuromorphic type computing applications, not only with memristors, but also in traditional CMOS type applications. And finally, how do we put things together in an ecosystem for machine learning? I hope you learned a little bit about our Streamlined machine learning architecture and some of the capabilities that could be come out of that ecosystem type development. So with that, I'll end. I think there's a couple minutes for questions. But really, again, thank you to the organizers for the invite and a chance to talk a little bit about here today in this talk about the things that we're doing in advanced computing architectures at AFRL.
So Dr. Hayduck, listen, it's great to see you. Good to see you again, and great talk. Really fascinating, important work. Thank you for that. I'd like to open it up to some questions.
Thank you, Dr. Brothers.
I've got one question for you coming up.
Sure.
What do you see as what are you working towards as a timeline for implementation of these technologies in a way that impacts the warfighter?
Oh, great question, right? I love that question. So different timescales, and my apologies for not mentioning it along the way. So certainly, the near-term technologies for Streamline ML, it's going out there right now. We actually had a transition with the Air Force Weather Agency, so they've taken on some of our work. You might imagine that as you're looking at weather, across different parts of the world, and certainly in areas, that you don't have weather underground apps that'll work very easily there. So you need very sophisticated models and things that you can take advantage of machine learning for. So they're taking advantage of our Streamline ML and deploying it right now. So we're very proud of that. So near term, quantum, farther term, right? Certainly, the field is moving very fast. But we look at within the DoD, we always talk about within 5 years or so, we can certainly see clocks and networking clocks and sensors having near-term applications. And in fact, we're doing a demonstration in 2022 in the Pacific Rim at the RIMPAC exercise, and how we can look at some technologies for alternative PNT. A little further out, certainly would be computing and networking. We think that within 10-year time frame or so, we're certainly going to be able to have practical quantum algorithms that are out there. So it's certainly not going to be a maximum utility, but certainly things out there that hopefully will show a quantum advantage. And we know the technology is going to continue to scale. That's the really exciting part is, the commercial world is moving so fast, especially with all the investment going on right now. So I think things are going to come along faster than we even thought about a few years ago. And then finally, the networking piece, 10 years plus, I think that's going to be a really tough nut to crack for us because there's so many components that have to go into it. but we're taking incremental approaches here at Afrl to be able to develop it. And last, neuromorphic computing, nano computing, we see some applications out there right now. So if we look at things like CMOS implementations with things like the IBM True North, we've done field demonstrations, real intricate field demonstrations at multiple locations, multiple instantiations, multiple architectures, if you will. So that technology is really, ready to go. I think there, memristors and how you integrate more towards an analog type of computing architecture are a little further out. Great progress has been made even in just the last few years of being able to have reliable operation out of memristors. Now I think the key is how you reliably integrate them. So things like the ARAP program are going to be very critical for that, as well as the industry push. I know there's different things like phase change memory being worked on for similar type of applications in neuromorphic. So I think the field's going to continue to push that, but it might be a little further out from that. And as I said, the next generation of True North being the North Pole, hopefully we'll have some results on that. But hopefully that gives you a pretty good time frame. And we are in Afrl, we always like to view things as near, mid, and far, and certainly have, if you will, departure points along the way where we can actually push things out to the warfighter.
I've got a couple of other questions that have come in. What is the relationship between SML and current planned JADC2 exercises and Abms convergence activities?
Great question. So our team is very tied into JADC2. And in fact, here at Rome, JADC2 is one of our drivers is really the applications. So joint all domain command and control. When I talked about the C4I and cyber, the command and control piece of it, that is really actually really points towards JADC2 now across all the domains, command and control. Interestingly enough, one of our subject matter experts on the Streamlined machine learning is our lead for the C2 area. He leads our strategic investment portfolio for that, Dr. Seversky. So what I'm getting at is we're very tied into the JADC2 community. Streamline ML works very closely with the Joint AI Center at OSD. And in fact, Streamline machine learning is in some of those. ABMS, it's something that's been a focus for us here within AFRL as well. That's gone through some changes. It's moved away from the different one type architectures, if you will. But certainly a lot of our technologies are feeding into it in the different areas as well. So really excited about that because that does give us a really nice avenue for our technologies as they develop.
Excellent. Another question, aside from trapped ion and superconducting qubits, anything being done on nitrogen vacancies or other types of qubits?
Yeah, great question. So I didn't have enough time to go into that today, but that's a really nice lead in. So nitrogen vacancy defects, our materials and manufacturing directorate at Wright-Patterson Air Force Base is actually working some of those different technologies and specifically nitrogen vacancies. So as those continue to mature, we'll certainly do trade-offs, but we're excited, certainly to be looking at different qubits, not just the superconductors, the ions, and the photonics. I think, you never know what can emerge as one of the leaders.
I think we're out of time. So it's really a pleasure to see you and thank you so much for the presentation. Very insightful. And it's a great lead into our next panel. So thanks so much.
Awesome. Thanks again, Dr. Brothers. Great seeing you.
Good seeing you, man. Take care.
Bye-bye.
Welcome back. Thanks for joining us again. So we just heard from Dr. Michael Hayduck, and I think he gave an excellent introduction to this next panel, right? He talked about some of the specific problems the Air Force has. He talked about some of the newer developments that they're coming up with. And that's what we want to start today. So before we get into later today's conversation about the convergence of AI and quantum, we really want to talk about the state of quantum computing right now. So we're going to explore the recent advancements and where we are right now as a launch pad for the later discussion. So what I'd like to do right now is have our panelists introduce themselves and give kind of a brief introduction to the kinds of work they're doing right now. So I'd like to start off right next to me here. Sir.
Hi, I'm Tyler Sutherland. I'm a assistant professor at UTSA. I focus on the theory of building a practical quantum computer. So what I try to do is I isolate the individual sub operations that you would need to be able to perform in order to make right now I'm focusing on trapped ion quantum computers. So for example, you need to be able to do 1 qubit gates with very high fidelity. We can do that now, especially if we use microwaves. 2 qubit gates with very high fidelity. So I work on the theory for that, which essentially comprises making a list of the things that go wrong with the gate and saying, all right, let's design a gate that is immune to that source of error. If you can do that, all right, the next highest source of error, figure out how to make a gate that's insensitive to that without compromising the first source of error. You try and make as far as you can down the list, ultimately resulting in hopefully not too difficult to experimentally implement higher and higher fidelity gates. Other problems in this regard are moving ions around. With ions, there's a lot of technical reasons why QCCD or quantum charged coupled device would be useful for making a scalable quantum computer. But what that essentially means is that you label zones in your quantum computer and you have the qubits themselves move from one zone to another, each zone having a specified purpose for the ions, and then implementing like an entangling gate in one zone and then moving them back to say like a storage zone. But the ultimate problem there is being able to move the ions around very quickly without having them heat up, which is its own separate problem. So things like this kind of are what make up the focus of my research. So I'm a theorist. I don't do any experimentalists. I make friends with experimentalists. I try and internalize the problems that they tell me, and I try and internalize the tool set that they have, which as a theorist means like, all right, well, we can make these numbers or these Rabi frequencies, these numbers, and then I take that in and say, all right, well, this is the set of Hamiltonians I can work with that are experimentally realistic. What can we do to move forward in making a trapped ion quantum computer, given those physical constraints? What I don't do as a theorist is, and this is a little unique, is that I don't focus on the algorithmic side of things. I don't think about Shor's algorithm or error correction and that sort of thing. My background is as an atomic physicist, quantum optics in particular, and luckily that gives me the exact type of tool set I need to tackle these types of problems. And unfortunately, there aren't enough theorists working on these types of problems. So, which is fortunate for me because I'm not competing with as many people. But so yeah, so that is the general goal of my research, to try and see where the people who are making the hardware that needs to be significantly better than it is right now in order to have practical quantum computers, and then kind of move us forward in that direction by solving problems from a theoretical perspective. The other thing that I do is I try and develop useful quantum simulation tools that would be implementable on NISQ devices. So kind of within the next 5 years, things that could be done with trapped ion platforms. I try and develop what are called analog quantum simulations. So they're like quantum simulations where you just turn on the fields and they imitate a more interesting Hamiltonian than a trapped ion Hamiltonian. But all of these are kind of geared towards like moving us forward to a practical quantum computer, and B, making the set of uses for quantum computers closer to where we are now. So that's sort of what my research entails.
Really appreciate that. Let's go over to Dr. Alarcon. Did I pronounce your name right?
Yeah, it's Lopez Alarcon. Yeah.
Thank you.
So I actually had a very short set of slides, if I can share that, to talk about my work. Hopefully you can see them now. So I'm in the computer engineering department in Rochester Institute of Technology. I've been a professor here for a few years, and I have to say that I got to computer engineering after studying physics for my BS and MS. So I do have some background in physics, and that's the seed of my interest in quantum computing, right? I teach computer architecture related courses, and I'm also teaching quantum computing, a graduate level course. So as a person who has been teaching computer organization for years now, I always look at the software stack from, where you start from the application and you go through all these layers until you are able to tell your hardware what to do. And there is a very strong parallelism between the quantum software stack and the classical software stack, right? So that is very, very similar. The one piece in quantum computing that I'm interested in is the compiler. And I do see also some parallelism in the compilation process of quantum computers with the implementation of hardware on the FPGA. There are some steps that are very similar. It goes through this decomposition, optimization, scheduling, mapping, and then finally generating the fault tolerant synthesis. And at that point is when you actually interact with the hardware and tell it what you want it to do by sending the control pulses that are going to manipulate your quantum system to solve the problem. And one thing that is important to notice here is that all of this is actually done in the classical world, right? So all this development is classical. Of course, the thinking is quantum. There is no getting to this point without thinking in a quantum way, but the actual computational process that you have to go through before you get to that point is done classically. Another piece that is important that is also classical and is important at this point of development is the circuit simulation. And I'm not talking about quantum simulation of the Hamiltonian, which is a different thing. I'm talking about simulating the circuit to check for correctness, to check for the behavior of your implementation. And it is very important at this point because you are able to abstract the noise and the error. And that is also another classical component that is necessary at this point of development to get forward, right? So I want to talk about basically the three challenges that I'm interested in and that I'm working on. On one hand, I think it's a great challenge to talk about the scalability of this, as we all are expecting that the quantum system is going to grow in size and we're going to be dealing with a lot more qubits. I'm wondering how the system, the classical portion of it, the classical pre-processing that we need is going to scale, right? And this is a problem of, at the compiler level, we see optimization and graph problems that need to be solved. If we talk about the simulation, on the other hand, what we have is matrices and tensor problems that are very computationally intensive, but also that use up a lot of memory. One other issue, obviously, that we all have in mind is the noise and the error in the quantum systems, in the actual physical system. And of course, the big strides are being done to reduce the actual error and the actual noise. But at the compiler level, there are things that can be done to mitigate the noise. And also, there is a question to ask of whether we can have some tolerance to noise, since we don't rely on a single outcome of the circuit implementation, but in a probability distribution. So what is the tolerance to noise that we can handle? And of course, the last one, since I'm teaching, is the pedagogical challenge, right? Of how do we teach our future quantum computing engineers or quantum engineers these skills, right? So I see there is a gap for the students when I teach them the GPU architecture. There is this step that they have to take from thinking in for loops to thinking in threads. And in quantum computing, I think the gap is much larger, right? I can tell them stop thinking in for loops or threads, start thinking in superposed states, but that doesn't even capture the unique features of quantum computing, right? So I think this is another interesting challenge that is worth looking into. And so that is in a nutshell what I'm working on. And I can stop sharing my screen now.
Thank you so much for that. Dr. Hubble?
Oh, thank you, Dr. Brothers. I have some prepared slides as well. I'll share those. I should say that it's an absolute pleasure to be here on the panel with Tyler and Sonia. My name is Travis Humble. I'm at Oak Ridge National Laboratory. That's a Department of Energy Research and Development Center in Tennessee. My role there is Deputy Director of the newly established Quantum Science Center. This is one of the nation's 5 National Quantum Information Science Research Centers. It's actually a partnership of 16 different institutions across the country. And our goal is to realize the potential of quantum science to assure American scientific leadership and national security. And the way we're doing that is we're taking advantage of the Department of Energy's leadership class facilities, like the spallation neutron source and the high performance computing systems like Summit, soon to be upstaged by Frontier, as well as the uniqueness of our facilities for fabricating and developing quantum materials. And in the bottom pictures here, you see an example of ion traps. Tyler was giving some excellent background on this earlier. And that is, I would say, one of the leading technologies right now for the development of quantum computing. But there are other materials that may be useful as well. Quantum spin liquids, like the ruthenium chloride crystal you see on the right, is one that we're interested in at Oak Ridge in the Quantum Science Center because of some of its unique properties for resisting the types of noise that Sonia was just describing. So overall, our approach is to develop these new quantum technologies to accelerate scientific discovery and innovation. And I want to just maybe motivate why we think that that's the right mission to take. Oh, I'm in the wrong spot, sorry. It was about 40 years ago when Richard Feynman made this now infamous quote that if you want to make a simulation of nature, you'd better make it quantum mechanical. And I actually take a lot of stock in this statement because when I look at the types of scientific computing challenges that we face at Oak Ridge, many of these models are rooted in the physics and quantum mechanics that describe nature. Whether it's astrophysics, material science, or chemistry, it's quantum mechanical models that are driving the computational challenges. And Feynman pointed out that if we could control nature at the quantum mechanical level, we could actually prepare this type of a computer to do these simulations. But he goes on to say that it's a wonderful problem because it doesn't look so easy. And I guess I should be grateful for that because it's kept us busy for over 40 years now. And I anticipate for 40 years into the future as well. The challenge, of course, is how do you actually control nature at this quantum mechanical level? And today, I would say that there are many different approaches that are underway. The atoms and ions, superconductors, semiconductors, and topological materials are just 4 examples of the different ways people are approaching the quantum materials needed for quantum computing. But you'll see down in the bottom 2 rows examples of devices that are available today for testing and evaluation for these principles. And so the types of software stacks that Sonia was just describing are actually able to drive the quantum physical behaviors that are embedded in devices like the ones you see here. Of course, there's the ion traps, Honeywell's QCCD architecture, the IonQ architecture, others for superconducting technologies from Rigetti and Google and many other places. The one within the Quantum Science Center that we're looking at is on the far right, topological materials, which have a natural resilience to the types of local errors that can actually throw havoc into quantum computing. And so we're using all of our expertise in material science and in engineering to try and develop those particular types of qubits. But in the meantime, we're taking advantage of what's available today. And within our Oak Ridge Leadership Computing Facility, the same facility that houses our high performance computers, we have a quantum computing user program in which our scientists can get access to the latest devices from IBM, Rigetti, and Honeywell, as well as others. And the point here is to try to understand how we should use these noisy intermediate scale quantum computing devices for demonstrations of quantum computing principles. And this gets into the idea of, is there a quantum advantage? Can we actually today find a problem that a quantum computer today could solve faster than a supercomputer? I think that that may be the wrong question to ask, and I hope we get into that during the panel. But it hints at the broader question of what are the applications of quantum computing? Certainly things that have quantum mechanics embedded in their description, chemistry and material science, like the chemical reaction shown at the top right, or this cartoon picture of the quantum spin liquid material we were talking about. But there is also a way to transform those models into problems related to, say, logistics, combinatorial optimization, machine learning, and of course, artificial intelligence that we'll hopefully talk about. So I think right now, the question of the applications of quantum computing, what is accessible, what is within reach today, is one of the leading questions in the field. So again, just to summarize, at the Quantum Science Center, we're very focused on the development of the next stage of this technology, as well as exploring these particular avenues of development, including quantum simulations, the development of new hardware, and then ultimately the demonstration of these types of applications. So thank you very much.
No, thank you, because what you did is you gave me a great lead in to actually the first question, right? So the first question, and what I don't want to call on folks, it's just have a conversation, okay? So you mentioned, applications, and that's kind of the first question I want to ask, because there's a lot of applications that we could talk about potentials, right? So we heard from Dr. Hayduck, he has some Air Force applications, quantum timing, quantum sensing, these kinds of things, quantum encryption, et cetera. What do you see, each of you see as some of the near-term quantum computing applications from your individual perspectives, theoretical, et cetera?
Well, I'll take on that as a first stab, because for us right now, the scientific applications, the ones where the mapping of quantum mechanics into the application space and vice versa is actually the easiest to have a conversation about. When you want to talk about quantum computers, it turns out quantum chemists, quantum material science, they often already know that language. They understand the limitations of the device themselves. So at least personally, I found those conversations to be the most easiest, Where it becomes a little trickier is when you start to move outside that domain where quantum mechanics already has a foothold. When you want to talk about the combinatorial optimization, turns out there's some really good arguments for why that's a great problem to look at, but it requires a little bit of different language in order to communicate those ideas.
Sonia?
So through conversations, when I talk to people who actually have PhDs in physics and not in computer engineering like me, I realize that we envision applications in different ways, because to me, an application, I'm just seeing it from the computation perspective. And so I'm looking at what applications you can run a quantum computer. Of course, there are the applications like the networking, quantum encryption, and so on, that are beyond quantum computing. But it seems to me like within quantum computing, one of the applications that naturally fall in this area is the Hamiltonian simulation that can be used for molecular solving problems with molecules, for exploration of new drugs. So it seems like naturally that is something that can be exploited, and I would bet that will be one of the first things to show some significant advantage or some advantage in quantum computing.
Yeah, so this is probably the most important question our field has to answer, but it's also one of the hardest to answer because it's a fundamentally uncertain question. So I think it's important to kind of just talk about the constraints on like what a near-term application of a quantum computer would have to have, the qualities that it would have to have. Well, one of the things we know about our first near-term use for a quantum computer is that, well, it's probably not going to be able to do error correction. So it needs to be an application that can have some sort of uncertainty in the output. So questions where the computational problem you're trying to solve is complex enough for classical computers not to really be able to solve it as efficiently as you'd like, but where you can have some uncertainty in the output, you can deal with some sort of errors that ultimately just result from hardware issues. So things like optimization problems, there are some recently a lot of algorithms such as like QAOA have been proposed that sort of only involve making Hamiltonian. We know how to make the icing model type Hamiltonian. You can map problems that people are interested in onto this this system that you don't need the type of system where you would need like error correction for it to do like Shor's algorithm or something. So like things like molecular simulations, optimization problems, those are the type of problems that are likely going to be first. It's difficult to say which one of those it will be, but you can say certain qualities of the application, and frankly, there's some of the most near-term application might be something that people haven't thought of yet. So yeah, just a couple of constraints on it. It's probably the near-term first use of a quantum computer is probably not going to need error correction. It's probably going to be some sort of analog simulation, so something that doesn't need a big series of gates. And it's a problem where you can have a lot of value in an approximate answer. It would be the main constraints, I would say, on a near-term application. But getting more specific than that, I would have to pretend to not be guessing.
I appreciate that. Could you, so we do have, I think anyway, we do have different types of folks in the audience, right? Some folks are software and doing AI, other people in quantum, and each has a different language. So one thing, if you could, just for the audience, Hamiltonian is fundamental to theoretical quantum mechanics, right? Could you just explain to the audience that may not know what that is, since we brought it up a couple times, what a Hamiltonian is and why it's important.
Hamiltonian is a mathematical object that describes the energy of a system. It's in classical mechanics too. In classical mechanics, it essentially is a formula for adding up all the different types of energy in a system, and that's kind of what it means in quantum mechanics. From the way I think about it, the Hamiltonian is the thing that moves the universe forward in time. Quantum mechanical system you're talking about forward in time. It's a precise description of how your experiment will change with time. And it's nice often because it's pretty easy to write down, even though the results of a lot of Hamiltonians are too complex. Most Hamiltonians are too complex to simulate in a classical computer. But that doesn't mean that we can't, in a pretty, just like an inch, write down the Hamiltonian of this thing we can't simulate. Anyway, so it's a mathematical description of, classically, it's the energy of a system. Quantum mechanically, it's the energy of a system too, but that is also tied in with the concept of predicting how a quantum mechanical system will move forward in time. So in some sense, it is a mathematical description of how a wave function, a quantum mechanical system will change as you go forward in time.
Thanks, appreciate that. Appreciate that. I think Travis, you brought up earlier this concept of quantum advantage, and you said you'd like to get to that, and I'd like to get to that right now because the promise of these systems, not regardless, but in some applications, is when we reach this quantum advantage. So if you could define what that is, and then let me get your thoughts on that. Why is that not the right question to be asking, as I think you posed?
Yeah, great points. So quantum advantage itself is a bit of a concept that the field is trying to look for a good definition. But in general, the idea is, can a quantum computer outperform conventional computing? And that's actually a fundamental theoretical question at the moment. We don't know that quantum computers themselves are fundamentally more powerful than classical computers. We have some good evidence where they are expected to outperform them. One of the best examples of this is what's known as Shor's factoring algorithm. Given an integer, a string of digits, can you find the two numbers that when multiplied together produce that digit? And that actually is an incredibly important practical problem because it underlies a lot of our cybersecurity mechanisms. But from an algorithmic perspective, there actually is a best known classical algorithm, a conventional approach to solving that problem. And a quantum computer can, at least in theory, solve it much, much faster. I mean, to the point that many people are very concerned that the appearance of a quantum computer would threaten cybersecurity. But whether or not there actually is a classical algorithm that could outperform the quantum computer is still unknown. So this whole field, this whole question of what is quantum advantage comes down to a demonstration. Can we show that the quantum computer, side by side with its classical counterpart, performs either more quickly, more accurately? My favorite is, using less energy. That's actually an incredibly important point. And to date, there have been about 3 experimental demonstrations where a quantum computer solved a problem faster than what was considered to be the world's most powerful supercomputers. One was actually the Summit supercomputer at Oak Ridge. This was a demonstration back almost 2 years ago to the day when the Google research team demonstrated a quantum processor based on superconducting qubits that solved a synthetic benchmark problem. And they showed by comparison that the classical computer, the Summit supercomputer, would have taken years to solve that same problem. And that was fundamental demonstration of what quantum advantage would be, because they did it in just a few seconds. But it was a synthetic benchmark problem. And it wasn't a chemistry problem. It wasn't an optimization problem. It wasn't a simulation problem. And so we're still looking now for an example where we run on today's quantum devices and we solve one of these problems, and it outperforms every expectation that we had for conventional computing. So I may have wandered a little away from your original question, but at least I hope that gets us started on the discussion.
Yeah, sure. So, Son, you want to chime in there? What are your thoughts?
So thinking about the quantum advantage, what came to mind is, well, there have been already experiments, as Travis was saying, that demonstrated quantum advantage, right? But I'm looking farther in the future, thinking, to me, real practical quantum advantage will be when we have an actual solution to a somewhat practical numerical problem that is solved, as Travis was saying, either more accurately or faster, right? So I think to get to that point, we need numbers in the qubits or the whatever the unit is that we use for the quantum information, right? And so I will see that happening when we have large systems that are, I'm not saying obviously without error, but tolerant to error to some extent, right? So to me, that will be true quantum advantage. At that point, when you have an actual numerical problem that you can solve for a size that is significant, and that it will be fault tolerant, and it will surpass, the accuracy or the performance of a classical computer.
And what do you say from a real theoretical perspective? How do you think about this?
They addressed the question well. The only comment I would add is that the question of quantum advantage implies sort of tacitly that the purpose of a quantum computer is to solve problems that a classical computer solves, but just more efficiently, which is to some extent kind of a narrow scope of the potential applications of a quantum computer, because really it's a different technology, and it will probably be useful for solving problems that we didn't think of solving classical computers for. An example I always like to bring up is the example of the laser. The laser is not a better light bulb. It's a different technology that you use for different purposes. And I think some of the way that this is talked about is missing this kind of point, that this is not a better computer. This is, and certainly not for like serial most tasks. The gate operations that we can do on quantum computers are slower, especially the ones I work on. And it's not obvious that they're ever going to be faster. There's just certain types of problems that you can show that we already know about that a quantum computer is better at solving. But more broadly, this is just a information processing device that behaves fundamentally differently. And I think once we start off from that assumption, we'll find there are a lot of uses for a quantum computer that aren't just better versions of what a classical computer do. They're just fundamentally different ways of maybe solving the same broad type of problem. But it's not going to be like, all right, well, this is a convolutional neural network, and a quantum computer is square root of n faster than a classical computer. It might be that, well, we are solving the same general type of optimization problems with a quantum computer, and it ends up being better, but it's not that describable as like an exact parallel where you can say like, all right, well, this has quantum advantage. This is a better way of solving this specific problem that we have been trying to solve with classical computers. There's just, I think that framing misses the kind of, there's, infinitely many problems potentially that a quantum computer could solve. And if we limit it to problems that classical computers solve, then we're kind of decreasing the probability of finding useful tasks that this machine is good at solving.
Can I pull on that a little bit? Because you mentioned earlier some guardrails that you want to establish for near-term things, where you don't have error correcting, potentially analog problems, where there could be some error, right?
Mm-hmm.
Can you give us some guardrails on the kinds of problems you think quantum computers are best at, just in general? Because you said there are a number of areas where you kind of think about. I know Sonia mentioned molecular biology and these kinds of pharmaceuticals. I'm extrapolating from that. What are your thoughts on that?
So yeah, it's a good question, but it's hard to answer being really vague. The general type of problem that quantum computers seem like they're good at solving is problems where the input is small, and then the computational space in the middle is big, and then the output is small. So things like where you're not having to load up tons and tons of data into this machine. It's not necessarily true that it's easier or better in any way to load data into a quantum computer than a classical computer. So things where it's a difficult calculation to do, there's a lot of internal complexities to it, but it's not like that in a way that you have to input a lot of information into the machine. Wave functions can get really big, and you can manipulate them, and you can kind of broadly see how there are a lot of really complex types of calculations that a quantum computer would be good at that a classical computer wouldn't be. But then you also have the constraint of reading it out, which you can't have the readout be really complicated too. There's not an advantage to, there's a big disadvantage to reading stuff out in a quantum computer. So that's kind of just the general description of the type of problem, I would say. But there's a lot of information processing that needs to be done, but not necessarily at the beginning or the end of the calculation.
Got it. We're going to go to the audience for questions in just a second, but before we do that, I do want to ask one more question. There's been a number of developments that have come out in the literature recently about, these huge advances in quantum computing, whether it be quantum coherence, increasing that time, quantum memory. I just saw something the other day about the barren plateau problem. What do you guys think are the most important developments recently that are really pushing this field forward? Perhaps, go ahead. Sure. Go ahead.
Probably the advance that, at least obviously I'm biased in this, the advance that had me the most excited about the prospect of making one of these machines scalable was when Honeywell demonstrated the QCCD architecture a year or two ago. That is, that's an idea that's been around since like the year 2000 or so. And it's really, especially with the way trapped ions work, there are technical reasons that you need to be able to do this. But just broadly, it allows you to segment your computer and think about, all right, well, we got this thing to work. Let's add more of them. It's kind of, when you think about going forward to a bigger and bigger machine, that's really what you can't think about this in terms of like, all right, every time we like increase the size of this thing, we're going to have to like go back to the drawing board and invent a new machine. At some point, it's going to be segment. You have little blocks of a machine that work, and you put more and more of them together. And that's one of the main things that the QCCD architecture kind of broadly allows you to do with trapped ions. And there's a lot of reasons for like gates and readout and that kind of thing that it's also advantageous. And I think that's the main reason that the highest quantum volume that's been demonstrated right now is Honeywell. And they've given themselves more gas than a lot of people by doing this, by taking the time and effort to not put a lot of ions in one big chain, and increase the number of ions. This has kind of a broader way for a more sturdy way forward in terms of like segmentation and building this thing up. And yeah, so that the demonstration of QCCD by Honeywell, I'd say, is probably the biggest technical step forward for me.
Travis, your thoughts?
Yeah, I think there's actually been a couple major shifts in the field that have enabled the successes that we're seeing today. The first, and this has probably been over the past decade, is the availability of quantum computing devices on the cloud. I think IBM and D-Wave were the first to actually make their systems available, but now others, many others, almost everyone is doing that as well. And that really spawned partly the imagination of what would be possible, that the technology was getting to a point where you could, in some sense, through the cloud, touch it and do some demonstrations. And we've seen an amazing amount of good papers and research come out of that. The other piece here is the development of the tools. Sonia gave a great overview on this, that are enabling people who are not experts in quantum physics, people who are unfamiliar with the concept of Hamiltonian, can in fact still program these systems and make progress on the development of ideas and applications. So I think those two things together are partly responsible for where we are today, why this is such a hot topic and why it's continuing to grow. But the piece of the technology that I think is probably most interesting to me at the moment is this question of how do we evaluate the utility of the technology. For a long time, it was, the number of qubits, the number of basic information storage units that we have in a device. But the truth is, we're starting to realize that alone is not the right metric. And so this question of metrics and benchmarks, what to measure and how to track progress, I think is really interesting, because depending on what you pick, right now you're seeing some very rapid growth in this technology, and I think that's really exciting. And then all of that hints at the idea that maybe we're moving towards this threshold of quantum advantage, or maybe we're not, and we're getting to the point where we're able to make those assessments. And so I find that very useful and exciting.
Nice. Sonia, your thoughts, and then we'll go to the audience.
So I was just going to mention that I agree with Travis. I think having the quantum computers available in the cloud has opened a world possibility to people out there. It's also really hard to keep track of the new advances that are coming out. There's so much happening that every day you wake up with something new and exciting that has happening in quantum computing and quantum applications, right? To me, anything moving forward with the error correction, error mitigation, error reduction is very important, I think. I think that's going to enable a lot of progress, but also things related to the connectivity of the systems, like Taylor was mentioning, when you have a multi-core, basically quantum device connected with each other, which also involves the network application or the quantum network application, in the way you need that to enable multi-core systems to be able to grow in numbers and other creative ways to facilitate connectivity among the quantum bits or the qubits. And so all of that I think is important. And there has been a couple of, like, looking at the news, I know both Travis and Taylor had recent headlines in the quantum computing news, right? With there was a LAN in Oak Ridge, a quantum LAN in Oak Ridge, and the longest entanglement time without lasers, right? That were also great to see. So I don't know, I guess all of it, all the little pieces are moving the whole field forward. So that is all great.
Thanks so much. Tim? Yeah, you do need that, yeah.
I think it's very important that we still keep on studying quantum systems in the framework on how it connects to high temperature work.
Mhm.
And I think I fully agree. I really like what you said. I found that improvement is going to be localized on certain aspects that would require that you push the environment where we live in into the lower temperature from which you can manipulate particles at the quantum depth. And I think that that would take a lot of theoretical physics, a lot of new modeling, a lot of things that we do not know yet. And the coupling, I view the science of quantum computing, what may have been science or aerospace engineering maybe 40, 50 years ago, when they realized that to fly in space, you have to go verify gas dynamics, and you have to move into a new physics that no one had explored before. And they put for Monte-Carlo methods and for all of those issues that brought out a completely new science. And then there was a lot of discussion, certainly from the mathematical physics, but and a lot of groups that try to comprehend very clearly how you connect continuum mechanics to the statistical mechanics. And I think the process of going from statistical mechanics to quantum mechanics is grossly understood. And until people doesn't, so I think I would still put a lot of human resources into understanding that problem because it's the science future. I mean, the phones will have to run our body temperature. We're going to have them on the unit, but maybe there are infinite small units that may aid some devices that may fit into the next step of the system, right? I mean, I think it's like you said, in increments at small scale, and there's nothing we can see after past that stage at more. But the idea that you're going to place the iPhone or the smartphone by a quantum computing device today, that's it.
Yeah, and it might not necessarily ever happen as a use for quantum computers. I personally don't think the iPhone is ever going to be replaced with a quantum computer. I don't see why that would be better. for most of the purposes an iPhone is used for. But there are other uses for quantum computers that they would be used for. But yeah, I think you're also pointing out an important thing that isn't focused on enough. I think it's just that there's a lot of fundamental physics centered around this regime that we need to be able to understand in order to build these kinds of quantum technologies going forward. There's a lot of theoretical work, like working in the algorithm side of thing, and frankly, there's a lack in understanding the physics side of actually making the types of hardware and understanding how these things behave, how decoherence works, how to mitigate decoherence, how to control entanglement. How does statistical mechanics of around these types of devices work? And I think there's a lot of interesting physics that will just naturally come from, not even in terms of improving quantum computers, but just improving our understanding of physics, just from the fact that it's a very ripe environment for like an experimental theoretical feedback, because there are so many people trying to make these kinds of things. So physicists working in this regime also, it's just a really ripe opportunity for a theoretical experimental feedback, which is in a lot of fields of physics. Exactly, yeah. And a lot of fields, it's difficult to produce experiments, or it's expensive to produce experiments. But I personally believe that the point when theoretical physics advances the fastest is when it is able to very quickly kind of have a back and forth with experiment. It's kind of such an obvious statement that I don't need to argue for it. But so yeah, I do think there is. You're right that there's a lot of branches of physics that could do really good, important work that would both help the prospects of making a quantum computer, but also just help our understanding of mesoscopic physics. And yeah, and so that's a very good point. And yeah, and not enough people are working on these types of problems, I think.
So, Joe, thank you. We appreciate it. Travis, thank you. Sonia, thank you. Great panel. Thank you for the questions. Thank you for the answers, panelists. And hope you enjoy the rest of the day. Thanks.
Thank you very much.
Thank you. Bye-bye.
Hi, and welcome to the next speaker, who I'd like to introduce. This is Robert or Bob Niffenegger. Bob started off as a graduate student with me, actually, at Purdue, where he got his PhD in physics. Then after that, he went over to industry for a couple of years. He worked at IBM. Intel, yeah, Intel. For a couple of years, and then decided that he wanted to go work on the more academic side of advanced computing technology. Went and worked at MIT Lincoln Labs for a couple of years, where he did really important transformative work on integrated photonics. And now he is a new professor, assistant professor at UMass Amherst, where he's now starting a research group. And yeah, so that's I'd like to introduce Bob Niffenberger. Thank you.
Thank you, Tyler. I really appreciate the invitation to come speak. Tyler and I know each other from graduate school. He's a very good atomic physicist, and it's exciting to have him working on these problems, because I think it's important to really understand the atomic physics very closely, as we were discussing, to move forward. And in fact, he has. Recently, you'll see on my slides, he's pushed the envelope pretty far with an experimental team to have the highest fidelity 2-qubit gates ever achieved, which is quite a monumentous achievement, I would say. So thank you. All right, so today I'm going to talk about a different side of it, which is not just the quality of the qubits, which Tyler is handling, but the quantity of the qubits, and hopefully going hand in hand I'm going to talk about work that I did at MIT Lincoln Laboratories with a large group led by Jeremy Sage and John Ciavarini. I also worked with Jules Stewart, MIT graduate student, Dave Reins, who's a postdoc with me. Sherry was the MIT Lincoln Laboratories leader of the photonics theoretical division, and Dave Karras led the fabrication efforts, amongst many other things that they do at Lincoln. So I'd like to thank them. This picture here is actually showing a prototype for a quantum computer that is going to have laser light coming out of the chip. And so the little the lasers coming out of the top there are actually controlling ions right above the surface, 50 microns above the surface. And so laser light is coming in from the right through that optical fiber, which is arrayed in a fiber block array on the right, going into the chip, routing around in photonics in the chip, and coming out the top. So I'm going to explain how we do that and how we think this is really a scalable architecture for quantum computing going forward. So I should have a disclaimer. This work was all done at MIT Lincoln Laboratories. I've since graduated, so to speak. I am now starting a lab at UMass Amherst in the ECE department. If you know anyone that would be interested in doing PhD work with me, let me know or collaborate. Thank you. All right, so the outline, we're going to talk just a little bit about quantum computing, broad overview. We're going to get into the details of why trapped ion quantum computers are such a good qubit. We're going to talk about how integrated photonics are actually a great way to control ion qubits. And we're going to get a little into the future and where this could go and the runway that I think is pretty long for this technology to move forward. So I think everyone has to show this slide now, and AI conference is no exception. What I think is interesting, and I've been showing this slide for a while now, not just at AI conferences, is as Moore's law has ended, computational demand has accelerated. So the demand is increasing. So thank you very much for that. And it's been driven by these large AI consortiums, right? So the world needs more compute, as Intel would say. So I had a chance to work at Intel on the 7-nanometer process and really scale the front end. I was working on the gate oxide layer. And if you look at this transmission electron microscope image, you start to see the problem. The problem is you see the individual silicon atoms. And actually, if you look even more closely at the fin, this is actually an IMEC picture of their 7-nanometer fins. If you look more closely, you see the hafnium oxide is a few atoms thick, the tantalum nitride is only a few more, and the tinitride is about the same as the silicon. So there's multiple minimum atomic layers coming in for each transistor in the device. But that's actually not the problem, believe it or not. The problem is the via, the interconnects, right? Bringing down metal 0 to metal 22 is the problem, getting 20-nanometer vias to effectively work on every single layer and get them connected. So it's connectivity. And it's interesting that the same problem that's limiting CMOS is what's going to be hopefully the power for quantum computing is connectivity of qubits. All right, so at Intel, I had an opportunity to assist their quantum program a little bit. It's led by Jim Clark and Hubert George. And they've really taken the idea that you can embrace the quantum. The spin qubit in a FinFET has some advantages due to the confinement of the FinFET itself. So try to make them qubits. If you cool them down to 20 millikelvin temperatures, they can act like a very nice spin qubit. And a lot of people think this is the ultimate scalable technology because it already is at wafer scale right out of the gate. But there are a lot of challenges. It's very difficult to keep these individual electrons coherent while they're in the substrate, and it's very difficult to tune them, couple them together. There's a lot of challenges just because it's individual electrons in a crystalline substrate that are your qubit. So there's a lot of opportunities for noise to enter there. But it's still very, very promising. But more back to the more fundamental question, why would you compute with qubits? Why are we even talking about this? And I think a quote from Dirac helps us step back a little and say, his quote's kind of counterintuitive. Each photon then interferes only with itself. Right? So we think about interference occurring between multiple particles. But the double slit experiment shows us that's not really the only way it can occur, right? And so it's very interesting. We're going to talk about qubits, right? So this could be a different quantum state. And that's fine. I mean, it's not too crazy, I guess, to think a particle can go in two directions at once. But what's very interesting is that as you entangle more qubits, now they're both going in two directions at once. And that's where things start to get exciting, because as you multiply those permutations, you have more and more possible paths that are all coming out. And a lot of people describe this as a higher dimensional interference that's allowed as you explore this larger and larger permutation space. which is really where the heart of the power comes from here. And so to be more clear, an SRAM can store a certain number of bits, and Babbage's difference engine could do this, but a quantum ion chain here, showing IonQ's chain, it could, in principle, not necessarily in practice, but in principle, it could store this larger permutation space, which really starts to approach very, very large numbers. All right, so maybe we have some indication that we would want to, but does that mean we should? And so quantum speedups are next on the list. And I think Shor's algorithm is the classic example where if you have a very good quantum computer, it's going to be able to factor these very large integer numbers. And that's still assuming you have a very good quantum computer. Recently, I think Professor Andrew Childs at the University of Maryland has really been starting to sort these on which ones are doing the best. I think a lot of people assume that nearest term, if you can map the Hamiltonian of the physical system to a problem, that's going to be the best shortcut to some speed up. But machine learning is right on the list. I mean, it's a very natural vector system. There's a lot of similarities in linear algebra applied. But I don't necessarily have the expertise to comment on that. So I hope you look up his slides and his work to get more commentary. I specialize more in how to try to build such a system. DiVincenzo gave us this nice roadmap on how to do it, and he started with the hardest part, which is to build a scalable system. But you need qubits that you can initialize. They have to have long coherence times before they lose their quantumness. You need to be able to perform universal logical set on them and be able to measure them very, very high fidelity. So the leading candidates for a long time have been superconducting qubits, transmons, led by a lot of work. Trapped ions have recently started to surge, which is exciting. And of course, silicon quantum dots. They all have their different advantages and disadvantages. Recently, neutral atoms have kind of come out of as a dark horse, where they've been able to use tweezer arrays, where individual laser beams can trap individual atoms, rearrange them using the laser beams, and use Rydberg interactions, where you nearly excite an ionized state, but use that very large volume of the electron to have them interact at distance to get high fidelities, not as high as the others, but very promising. And photonics also, which is going to leverage nanofabrication facilities that have been used for classical CMOS photonics for a long time. So there's a lot of things that are happening that all have very viable qubits, but they all have a challenge in increasing the qubit number without losing performance, which is really everybody's difficulty. So where are we? The quantum computing state of play, so to speak, could be graphed out in many different ways. One way is to have the qubit error rate on one axis. So as we push down, we're getting higher and higher fidelity, more depth in our circuits. And as we push out, that's getting more larger qubit number that we can explore this larger quantum volume space. I think it's very exciting that there's been kind of hints of quantum advantage coming from these, as I might call them, card shuffling experiments with transmons, but nonetheless very exciting and very high fidelity experiments with large numbers of qubits. But I think a lot of people are starting to look at more of a universal hardware metric where you could apply it to multiple algorithms and see if, based on this metric, you could actually execute algorithms. And one way to do that is to quantify not just the number of qubits, but also the depth of the circuit you can execute with that, which is trying to explore that very large Hilbert space, that permutation space I was talking about before. I would love to emphasize that Tyler Sutherland here at UTSA has really pushed the axes on my chart. So thank you, Tyler. Him, along with the collaboration of Daniel Schlichter, has pushed this down to set the record for 2 qubit error rates. So I just want to mention that it's consistent with 0 error. So more experiments will tell the difference. Yeah. He's going to get mad at me. Okay. So if you use this quantum volume metric and you put it on a timeline, you can start to see that there's a very unique advantage coming out of these trapped ion experiments. As we were hearing, Honeywell's QCCD experiment, which is allowing us to move ions around, and IonQ's experiment where they have all the ions in a chain together. Both of these architectures more or less allow you to get full connectivity at every qubit, where transmon systems have to play a game of telephone if they want to talk to each other. And sometimes it's a one-way line. It can make it very challenging. So I think it's exciting to think about this metric for more practical applications coming forward, because it generally allows you to think about the algorithms you can execute. So a recent paper just came out this week, I think is really great, by Thomas Levinsky, plotting these together, where the circuit depth here, he's plotting the circuits kind of in a log a 2 to the n scale here for each qubit, showing this gray box, which is the qubit volume approximate for these systems, and showing then each algorithm that's executing and how it starts to walk out and need more resources in circuit depth or need more resources in quantum qubit number. I think this is amazing benchmarking tool, and I think it's really going to help us move forward and think about what are our nearest term applications going forward. I would say that you wouldn't want to directly maybe compare Honeywell and IonQ. These are the services available on the cloud at the moment. I think they have much more advanced systems in their test beds. But what's so special about IonQ is why are you able to do this? Well, they're very high fidelity operations. I mean, they have the record thanks to Tyler for the highest fidelity. Grade 2 qubit gates, 1 qubit gates. You can read them out with almost as much fidelity as you can imagine, depending on how long you want to wait. They have very long coherence times, so they can persist for, I think, hours. Actually, some instances they're all identical. You don't have to tune each one you get. They're the same right out of the box. You can move them around. That doesn't actually perturb the qubit state, and they have low crosstalk if you can focus lasers to them. And this actually already makes them the world's best clocks. And so I think when people talk about near-term applications for these quantum systems, it turns out sensors, and in fact, trapped ion clocks are definitely going to be the nearest term application of these technologies. So, because they already are the best ones. That being said, there's a lot of challenges. They are not in the solid state. You have to catch them. They can escape. They require many laser beams, multiple wavelengths. They have to be very stable and precise. You need to address them to each and every qubit or ion in the system. And finally, they're slow. Their gates are slow, shuttling is slow, remote entanglement of these ions is also very slow. And that's kind of a trade-off you get with this long coherence time. You can't have everything. If you're going to have a very coherent qubit that's resistant to any perturbations from the environment, that also means that when you try to do an interaction with it, it does take longer. So there's always a trade-off. All right, so let's get more into the details of how a trapped ion quantum computer works. So first, you have to start with a neutral atom. You can cool it beforehand, filter out isotopes you don't want, push them towards a location that you want to ionize it, rip off the electron here with 2 lasers, and then you trap it in a Paul trap, which I'll get to in a second. Then you have to start laser cooling it, and then you start doing qubit operations. So now these are the wavelengths we need for qubit operations here, where one wavelength is going to be doing the initial cooling of it. We're going to prepare the state, and the red 674 laser is what we're going to use to create the qubit, so that if the qubit is in the ground state, it's going to be fluorescing as we're shining on the 422. But if the qubit laser light 674 pushes it to a different electronic state, it becomes dark. And we're going to use those as our down and up, or up and down interchangeably qubit states. And then to detect them, we just look at the fluorescence of this qubit. So as we shine 422, if it's in the ground state, it's going to be shining. If it's in a different state, because the qubit light has brought it up there, it will be dark. So what does the trap look like? So a 3D Paul trap is a quadrupole. You can't trap a static charge with static charges. So a nice analogy is this rotating saddle trap, where you're always catching it as it tries to escape. And this, you can see kind of on the bottom here, if you take a 3D version of this trap and you unfold it to a surface, you create a chip like this, where you can have red axes kind of creating a cylindrical trap along the axis, and then you have DC effectively charge come in on the side electrodes to move it around, and you can actually shuttle the ions back and forth by just manipulating these electrodes. And this is what this looks like. This is a chip that was developed at MIT Lincoln Laboratories, again by John Ciavarini. And here, not to scale, but these are the ions that are trapped right on the surface. This is about a centimeter by centimeter chip. And there's actually been a lot of work on different nanofabrication technologies for these trapped ion surface electrode traps. There's nearly an innumerable gallery. I think it's very exciting. A lot of work has been done on this. But I think it is unfortunate that these architectures without the interconnects are kind of like making a front-end process without having your metal 0 coming in and getting your vias connected. Unless you can connect to each of these qubits in these chips, you just have a very nice front end, which Intel's had for a while. Their back end, those vias are really tough. So, so what does that mean? What do you actually have to do to get that connectivity? So Imagine you're an ion and you're two ions maybe, and you're sitting in a trap, you're happy in your ground state, and you're going to go through a 2-qubit gate. So you're starting in this trap where the ion with you is being repelled from you. 2 like charges are going to repel, but the harmonic confinement of the surface electrode trap is pushing you together, okay? But your interaction is going to be via this electric Coulomb charge. One laser beam is going to come in and flip you. So now you're in the electronic state that's dark. But not only have you flipped your electronic state, now you're wiggling. You have a little vibrational motion that you've been excited in this harmonic oscillator. It's like you're in a Newton's cradle, and now not only have you flipped signs, you're going back and forth. Now, at this moment, there's a juncture where we're going to have these 2 particles go in 2 different directions at once. One direction is going to go right back down. So not only do you flip your spin back down, or flip your spin back down with the other one, but you stop moving. But the other direction is to have the other qubit flip and also stop moving. And either of these superpositions are possible. And in fact, these 2 qubits do this together. So that if you measured what one was, you would always find that the other was in the same state. So this is just one special case of an entangled state with some details obscured. But this is the bread and butter of a Mulmer-Sorensen gate, which is a foundational gate for trapped ion qubits. This is a Hamiltonian describing it. I would just say that the A's in the parentheses there represent changing that motional state, and the sigmas next to it are the changing of the electronic state. What's important here is that both are happening simultaneously. Okay, so that's great. This is just an example of some calibration. These have to be very precisely tuned, and in our system, we were able to get 98% fidelity, limited by what we thought was vibrations. So it's not a trivial thing to get all the 9s of precision that Tyler did, but we're working on it. And with this and other single qubit gates, you can do a full universal C0 gate. All right, so I just told you 98% isn't easy. Let's go back to this chart and think about where our errors are and where we need to go. So there's been some recent estimates of how many qubits you need to have to do a Shor algorithm and how long it would take and what kind of overhead for quantum error correction you would need. And so the estimates are that you would need, 20 million noisy qubits, given the error rates that we have, all of which are mostly for redundancy and error correction, catching phase flips, bit flips, etc. Or conversely, you could just have 4,000 perfect qubits. It's not hard to get. So I think this the show Devs on Hulu kind of sums it up. Nick Offerman is getting asked by the protagonist, how many qubits is it running? And he answers, a number that seems pointless to express as a number, which the MIT campus group put on Twitter. The joke is that it was 2. All right, so they, nonetheless, we're pushing down to these perfect qubits. And again, I emphasize Tyler has been helping push this down to very low error rates. But nonetheless, we have to push in the other direction too and get a much higher number. I mean, even if we had perfect qubits, we're still going to need thousands. So what's the holdup? Well, it's scalable optical addressing. Right now, the state of the art is that you have laser beams coming in from the side of the trap. And this has really been a breakthrough. This is the state of the art. This is what IonQ and everyone does. They have multiple laser beams coming in from the side, and it still has runway. But you can imagine that at some point, if you tried a larger 2D array, that there would be a limit. You're going to have crosstalk between these different zones, and that's going to break down and cause errors. Not to mention, these systems are extensive. The optical laboratories are very complicated, and we really need to find ways to reduce this, have 2D addressing, reducing crosstalk, kind of have passive alignment. And I think the consensus is growing that this is a job for integrated photonics. So let me talk about that work done at MIT Lincoln Laboratories. So again, I emphasize this was fabricated at MIT Lincoln Laboratories. This is the same chip. This is a top-down view of a different chip developed there as well, where you can see that light is entering from the side of the chip into inverse tapered waveguides, routing through photonic waveguides in the chip, splitting into multiple channels, and coming out of diffraction gratings in the center. Here are 4 zones that all have the individual wavelengths necessary, all 6 of them, for these individual ion qubits. So a little more details about how that happens. We have optical fibers on the outside of the chamber. Those optical fibers come into the vacuum. They go into a fiber block array, and this allows the fibers to come right up to the side of the chip where they are shining light into printed photonic waveguides on the chip. Then these are routed around, almost like an optical fiber printed on the chip. And when they get to the center, then a diffraction grating will actually diffract that light out of the surface, and we can focus it in 2 dimensions using some curvature interpreting the period. This is done with silicon nitride, and this is a simulation done with numerical of that beam coming out. Again, these are all fabricated there. Dave Karras led the fabrication efforts. There's a lot of complicated things regarding sidewall roughness, etch uniformity, things like this, and he did a great job with that. And these are some SEM images of those chips during fabrication. Each waveguide is actually specified for each wavelength, so they all have different widths and different gratings for each. This picture here is kind of dull. It shows just the windows that we need for that light to come out of the chip. So it's just you're seeing these little holes. What's interesting about this chip, deliberately we put indium tin oxide only on 2 of the windows, left some bare to show that this dielectric that's exposed underneath the silicon oxide charges, and those charges directly perturb the ion and create a lot of headaches, which we'll get to soon. But we can mitigate it to first order with this indium tin oxide film, transparent conducting film. So this is what it looks like in practice. You have to attach the fiber block array. This is a first iteration, a little messy, but the epoxy is clear to see. So the light's coming in, routing under the metal on the chip, coming out through the surface. Again, different waveguides for each wavelength of light we need, and diffracting out at the top. You can also see the wire bonds for the electrodes. Now, to characterize these gratings, images had to be taken of each beam at various heights above the chip surface. So these images were reconstructed by me taking a microscope objective focused to the surface of the chip, translating it in small steps, microns at a time, taking pictures, and then superimposing all of those pictures together to create these beam profiles as all of the laser beams are converging at the spot above the chip where the ion is going to be trapped. This is another profile of the beam. You can reconstruct a 3D depiction of this if you want. And it's very important because you don't get a second chance to align your laser beams once you've created your photonic chip. It's one and done. And you can see we need a little work on our beam profiles. If you create a 3D reconstruction, let's see if the computer can handle this. Oh, I can't load it. Okay, interesting. Oh, there it goes. All right. So this is actual data, and if you look closely, you can see the higher order diffractions that are coming out the back in the wrong direction. This is a reconstruction of thousands of images of these beams, all showing how they converge just above the surface, and that's where the ion is going to be, 50 microns above the surface in this trap. So some packaging and installation. We use some strain relief to make sure that fiber block doesn't rip off, which is a main challenge of this. This is a picture of the cryostat that we use to cool this down with light actually coming out at you for the first time. Cooled it down, and after a few iterations, we got all of the operations to work. So we're able to photoionize and load the trap using integrated light, Doppler cool that ion and detect it, control it with sideband cooling and qubit operations, and do various repumping operations as well. And here, this is again another picture where the reason you can see the laser beams is because I'm doing cryogenic tests with liquid nitrogen, where water vapor is kind of seeping over the chip and allows you to see the scattering off of that. So you can see each color there. Yeah, so again, the ion is trapped right above the surface. This is kind of the far field of it. So when you detect an ion and it's only being illuminated from the chip, this is what it looks like. This is a little picture of an ion that is being illuminated with no free space beams. So the only reason you need windows right now is for detection, and for now, and that's it. We're still going to collect these scattered photons externally and detect them. But there are possibilities with chip. There have been recent demonstrations to do this integrated within the chip as well. We also did spectroscopy, where we use the qubit light and the light that has to bring it back down to the ground state together. Here, just showing some kind of trivial spectra of the motional sidebands where, of the harmonic oscillator. And further, we actually characterized each beam in situ by using these ion operations. So we had pictures already but can we do the ion operation various steps as we move the ion through each beam, and we can actually use that to profile each of these beams together, and they match quite well. I should note they're not on target. This used a different recipe for the film that changed the index of refraction, so they're not all at 0 here. They're a little off, but nonetheless, we could use each beam on the surface. One very important thing, again, kind of asking a more broad question, why would we want to do this? Unless there's wins in performance, it's not just the quantity that's going to take us the distance here. We need some quality. So an important demonstration here was that we found the integrated beam paths had resilience to any vibrations that perturb the qubit and ruin its coherence. So here we're actually deliberately defeating vibration isolation in the system so that the cryogenic cooler is vibrating the trap. So now as you take a long exposure, the ion is doing all these circles. And with the free space beam, it totally destroys the coherence of the qubit. Doesn't work. But the integrated beam, because it's moving along with the chip, doesn't mind at all. And as far as we could tell, it didn't degrade the coherence at all. But it's more consistent with a factor of 25. So, but I think it's important that you have these passive wins as you start to do integration, because that's going to be a downhill battle as we continue, and it can't just be uphill. All right, so just in summary, we were able to do all the operations, do integrated detection, and we had some vibration resilience, which is very exciting. So next, I think the natural question is, again, can you do more? So again, this is a chip developed at MIT Lincoln Laboratories for clocks by Robert McConnell. And here, just kind of adding each wavelength one by one, you can see how the different colors are all coming into each zone together. And you can imagine there's a lot of room on this chip to have a lot more zones. But let's take a smaller first step and just see what happens if we try to do two zones that are very close together. So here we had a test chip that was developed with two integrated zones very close. And let's see if we can do a fan out where we can have a single splitter take one channel of light coming into the chip in one fiber, split it on chip into two zones, and control ions using shuttling between them. So if we move the ions in and out of these two beams, can we use that to modulate the gate while we're pulsing the global qubit light coming in through one fiber channel together? I think this is a very important question for larger architectures. So what does this look like in detail? This is the schematic of the mask of the gratings, the two zones near each other. Rabi oscillations on single qubit worked well. Here's what a picture looks like zoomed in focus to the surface. You can barely see the windows, and the ion is kind of out of focus as a point source. It looks like a ring. You can see the grating emitting light. And so the first thing to do is move the ion through this and see what happens when you're doing a short pulse that could flip its electronic state. We see both zones, but we see that one zone is much stronger than the other. So that already hints to some problems we're going to have possibly with this particular chip. Nonetheless, we'll forge ahead. But we need more operations. As I said, we needed many wavelengths to do these operations, not just the qubit operation. But for now, let's do those with external beams just to characterize the qubit one integrated. So what we're going to do is shuttle the ion between the central zone where the external beams are and the two broad zones where the integrated beams are, and move them around. This experiment was not necessarily designed to do this fast or well, but we're going to try it anyway. So the first step is to load an ion in a single well, detect it, make sure it's still there. All right, good. We caught our first ion. Move it out to we'll set it aside for now, like a cooking show. We're going to get another one, load it, detect it, make sure we've got two. Great. Now put them into both integrated beams, pulse the global channel, and start the detection sequence. So we detect the qubit on the right first, we detect the qubit on the left next, and we cool it a little bit. And then we bring the first one in and cool it a little bit before we start the next cycle, and we iterate. So we can cycle through this very quickly. Once we have the two ions, we don't lose them. Not so quickly, kind of slowly actually, but repeat it many times. So this is kind of the QCCD procedure that I was talking about. This has really been embraced by Honeywell, and they've really it was a major breakthrough for them to do this. This is kind of a very simple schematic of what it would look like. they do much more complicated procedures. One thing that's interesting, I should mention that there's hardware on the classical side, control hardware that is open source called Arctic, developed by Labs, which is making this a lot easier for experiments to start. No longer do you have complicated LabVIEW. Apologize if anyone really likes LabVIEW. Systems that you can do. This is a Python code that's very easy to write pretty quickly that is starting to enable this to be a more flexible system to test with. So at each stage here, I'm actually detecting and verifying within the Arctic system using our hardware to verify each step before continuing. So the very first trivial experiment you can have is move one ion out of the beam. You still have two, but only do a Rabi oscillation on one. So the right ion you can see is doing some sort of electronic Rabi oscillation, albeit a very poor one. Again, this system was not designed for very fast transport protocols, but the next step would be to improve that, make them not only faster, but more adiabatic. Nonetheless, it looks pretty good. We do see some crosstalk entering from that ion that's supposed to be out of the beam. So it's interesting that already at this scale, we see some issues. So we're going to have to investigate that more in the future. And then the goal of this experiment was just to check, can we control these two ions and detect them at the same time? And we already kind of saw there was something wrong with that left zone on this particular chip. So the left ion did not complete even a full Rabi oscillation before heating too much, which is unfortunate. But so is fabrication difficulties. What are you going to do? We have seen on previous chips that subtle fabrication errors can introduce defects which effectively perturb the ion and would prevent high fidelity operations. Nonetheless, we did push the coherence a little bit up on the system, which is great. Again, due to that vibration resilience of the integrated photonic channel. All right, so the future. Looks like I'm gonna have lots of time for questions. The future of integrated trapped ion chips. So I should point out that this is not a one-off. There's been work at, for instance, MIT Lincoln Laboratories to do other integrated technologies. Specifically, previously, they've done monolithic integration of digital analog converters, allowing the control of the DC electrodes to be done with serial inputs, which is a huge step. You can imagine this represents a unit cell where the CMOS classical electronics could control the digital, the quantum qubit processor on top, which is pretty exciting. Recently, there was a demonstration to do integrated detection with wires that are superconducting, which is an amazing achievement. This recent development of photonics starts to really round out the thing, and there's more to come. I think it'll be interesting to see if microwave gates that Tyler has led pushing down to very, very high fidelities, low errors, if that microwave generation could be integrated in the chip as well. There's a lot of challenges with that, but it would be interesting. And there's also an interesting possibility to integrate the RF control of the chip that's trapped, or the trap RF field in the chip as well, but there's a lot of challenges with that, specifically getting high voltages on the chip. It's also a little sobering to think about this review that came out in 2016 titled 15 Years of Cold Matter on Atom Chip Promise, Realization, and Prospects. So, this is not new. There's a lot of challenges. Fabrication is very difficult. Packaging is really, really difficult. And, kind of getting everything to work at once is pretty tough. Nonetheless, I think there's a lot of blueprints to go, and photonics is really leading the way on what's possible, integrating and miniaturizing a lot of atomic systems, laser systems, which I haven't even gotten into how to miniaturize a laser system. It's all kind of a black box that we didn't talk about, the laser, but miniaturizing that as well is a huge prospect. I do want to point out some very, very recent results. At MIT Lincoln Labs, postdoc Dave Reens that I worked with presented this at DAMOP recently, that they have used avalanche photodiodes, which are a CMOS technology, not a superconducting technology, for detection of ions in the chip. So that will be a preprint soon. But also recently, Megan Ivory and the Sandia team have done a very similar experiment with integrated avalanche photodiodes on a chip at Sandia and also demonstrated detection there. So I think this is a really exciting time for a lot of integrated technologies in a trapped ion qubit system. And there's more to come. I think This is maybe a long-term vision for having more of these single photon detectors like we just saw with the avalanche photodiodes integrated. You can imagine running these gratings and photonics in reverse. Instead of just delivering light, you could be capturing the light as well. And once you do that, and it's in photonic channels, you could be interfering that light on chip also. Again, RF generation could be done, microwave generation could be done, albeit with challenges. Using a lot of photonics technology for modulation and switching would be very exciting. And once you're collecting light, once you're modulating light, once you're interfering light with photonics on the chip, you can start to imagine remote entanglement, either between nearby zones on the chip or different chips, which I think very, very, very exciting. And this then leads into the possibility for networking and modular architectures. It's a whole new route for scalability in the system, besides just this QCCD architecture. So I think it's really an exciting time. This, trapped ion qubits have always been, in some ways, the perfect qubit, lacking a home, lacking an integrated technology with which to build upon. And all the others kind of had the reverse problem. They started with an integrated technology foundation and tried to make a perfect qubit. And I think that coming the other way with a perfect qubit, as much perfect as it is, within developing integrated technologies, it's been challenging, but I think it's a better path long term. So as grand a vision as you can imagine is an infinite chain of ions, so I'll leave you with that. This is kind of a scale representation I made in Blender of what we can see. And so with that, I'd like to again thank the team at MIT Lincoln Laboratories and the opportunity I had to work with them on this. John Chiaverini is still the PI there. He's really had a vision for this for a long time. Jeremy Sage, who's the other PI on the project, has since been, I guess maybe promoted is a way to say it, to Director of Integrated Technologies at IonQ, so we wish him well. And Jules Stewart, who really assisted me with every one of these experiments, he's now at NIST doing his postdoc. So with that, I'll take questions.
Very nice.
Once the microphone gets there.
And there would be a CO1 that was in an old transistor, the work of Apostle 6 years ago was to apply a voltage. And you have on and off, but that is the technology has to be still maybe. So let me understand it a little bit. This is what I'd like to see. What you need is an ignition energy to make it. So you need to confine the ions, and so in a way you need to sort of put a trap and then have to untrap them, and so have it on and off. What is the driving of the energy coming from? So you can control the magnetic field instead of electric field by voltages, or you do somehow a conversion of some electric energy that.
Yeah, it's a great question. So it's quantum optics. It's the fact that laser light is doing the modulation. So more to the point, it's like, where's this modulation? It's a laser. Well, a laser doing what? Well, a laser that's going through a crystal that has a piezoelectric element that, as you drive the high voltage RF, creates a sound wave. And the frequency of that sound wave is added to the laser beam. So your laser beam becomes your carrier, and you add a modulated signal at this RF. And that is what's allowing you to switch ion, because you move it onto a resonance of an atomic transition, and it flips that electronic state. And there's lots of ways to do it. And I think it's exciting to think that, within one qubit, there's more than one way to slice it. One ion. So once.
Yeah. But then how is that also getting factoring of analog frequencies?
Yeah, I think that's exactly the question that my talk is about, is what are the steps? And I think what's encouraging is that, unlike other photonic technologies where loss is a direct limit of fidelity, these are just pipes, right? The light is just going through it like a pipe. If you have less of it because you have loss, in fact, our demonstration had a lot of loss, 30 dB. We've improved it significantly, various things I have to talk about. but 30 dB is a lot of loss. It still worked, right? And if you get 20 dB of loss instead, that just means that you can do your gates faster and you have more power budget to do more. It doesn't actually fundamentally limit the fidelities. So that I think is already a big win. What you're talking about, is this manufacturable to some robust system? I think there's more open questions about how do you get like a CMOS type of bit flip, where there's error rates on the order of the age of the universe, right, for a bit flips. I think quantum verification, which is some stuff that UCLA is working on, is the only path to think about that, where you do an operation and you try to verify it by screening out and shuffling out the other electronic states, seeing what's left there. Well, you hopefully have shelved your electronic state somewhere far away where it's not seeing this kind of shelving scheme. And only that verification mid-circuit is the way to do this robust thing that you're talking about, I think.
You need new materials or you have to benefit material going that far?
Well, that's the best part. I think the electronic structure is only still being explored and how it can be exploited in these systems. There's hyperfine levels, there's Zeeman splitting of sub-levels, and so in some sense astronomy gives you many different materials that you just have to buy lasers to control the different aspects of it. I think trapped ions really the main materials technology that has to be developed is regarding lasers, laser technology. I think that's what's a limiting factor right now. Cool. Are there virtual questions? Does anybody watch? It's exciting to have a live audience, but oh, there's one. How do you avoid saturation? Am I supposed to read it? Okay. How do you avoid saturation and overpumping with 1033? Yeah, so that's a good question. Someone really knows their stuff. So the short answer is you still have to do that modulation off chip. Okay, so that's the same modulation and extinction that you need to do off chip. So all of this, all the modulation was done externally from the chamber, like in other beam paths. So that's how. But I think it's going to be, that is exactly a problem. The extinction ratios you can get from photonic modulation is going to be a big problem moving forward. Okay, so I guess I should read this question. Yeah, okay. So you may have covered this, but this is how is it looking for stacking ions and layers above each other? Or are we still looking with linear configurations at this point? It's because of the complexity of the lasers being used. So this is a great question because recently neutral atoms using tweezers have been able to create 3D arrays, cubes of atoms. And that's really exciting because not only is that a denser structure, but you can actually have them talking in 3 dimensions for next nearest neighbor interactions. And the question is, can you do that with ions? I think there's a lot of people trying, and that requires doing complicated 3D traps. So I had a very flat planar trap for the ions, but you could imagine having electrodes that are coming out of the surface of the chip and doing manipulations with ions up there. But it's very difficult, and I think it has some prospects, especially for rearrangement, if you kind of run out of room for reordering things in this QCCD architecture, but otherwise I'm not sure. Great. Are there any more questions? All right. We're done? All right. Thank you very much.
Good afternoon. I have the pleasure of introducing our next speaker, Dr. Irene Gamba. Dr. Gamba is currently professor of mathematics and leader of the Applied Mathematics Group in the Odin Institute. She also holds the W.A. Tex Moncrief Jr. Chair in Computational Engineering and Sciences II, all at the University of Texas at Austin. Dr. Gamba is a fellow of both the American Mathematical Society as well as the Society for Industrial and Applied Mathematics. She serves on many different science advisory boards, including IPAM, SAMC, and MSRI from Berkeley. She has been involved with many different journals as various positions, including being part of editorial boards, and is currently the editor for the Bulletin of the American Mathematical Society, the Journal of Mathematics Fluid Dynamics, and in her credit, she's authored more than 140 research papers, and her work is currently supported and funded by both the NSF and the U.S. Department of Energy programs. It's my pleasure to introduce Dr. Gamba.
Thank you very much for this very nice introduction, and I'm very grateful to the invitation to talk in this forum. So I choose something that, coming from mathematics and coming certainly from applied mathematics and computer science, I want to talk about things that are really of interest to quantum computing in some ways, as much as some aspects of very theoretical mathematical physics that relates to issues on how you couple quantum systems to kinetics. And that was somehow related to the questions that I have to the two previous speakers and to the panel earlier today. So I will talk about most of the lecture will be about the topic on the Bose-Einstein condensate stability when you do a quantum Boltzmann couple to the condensate, and show that this is a model that brings together some components of kinetic theory as much as quantum mechanics. But in order to solve it, you have to have what we like to say in math physics or in mathematics for rigorous results, a well-prepared data. It's like this system, you cannot expect that everything inside was nice as the heat equation. When you just give a domain, give it data, you always solve it. This is not the case. You have to have a well-prepared data. And part of the analysis, if you wish, is related to that. The second one is some recent numerical result that I did on a quasi-linear diffusion problem on a magnetized plasma, which is, it's not a problem of quantum mechanics. It's a problem of a tokamak on the plasma physics. But the reason why I bring it to your attention is that once you get to see how is the way to calculate, right, or to interpret this model that has a stability, I can infer that the numerical scheme is going to be very much as the style of this model, because they are actually doing the same thing. They are looking at the probability density of finding particles in motion, but they are going to be coupled to a system which is the wave plasma equation, which is a much more microscopic element. And that comes as a dispersion relation into the kinetic model. And that actually is exactly what happens if you look at it, or in a sense, I will show you for the coupled system of quantum condensation. Okay, what is interesting in this is that we did the analysis for this problem. So this is a render picture from the French school, on which they have particles as well. When the gas is hot, the wave function behaves like a classical particle. You cannot distinguish. As you cool down the system, it starts to get condensated. And when the temperature gets to reach zero, it becomes a blob of the single wave. And that is described by the Gross-Bitaevsky equation. What happens here, this is a system that starts complete equilibrium, but your initial data is going to be a statistical Gaussian, also well prepared, because you cannot do the things with arbitrary data. And then what you have is that the effect of magnetization of the plasma induces an anisotropy, a very strong anisotropy in the probability density. And this is not due to electrostatic effects, as we always have done, or this is not a runaway phenomenon. This is really a magnetization. Okay, so let me start by describing the slides are a little bit dense, but I'm going to say a few things about them, and then I'm going to skip many other things. So, okay, so the bosonic gas dynamics below condensation temperature is given by a system that models the coupling of a quantum Boltzmann and a model of condensation in a very low temperature regime. And that couples then the Bose-Einstein condensate wave function that usually is modeled by Gross-Pitayevsky, right? In a system that is, in principle, the model is you are averaging the properties in a space. Okay, so you are really localized into the analog to the Bose-Einstein condensation formation, which is an isolated system on which you would expect the gas to get condensated. And so the Gross-Pitayevsky equation is going to be perturbed by kinetic probability distribution, by the average of the probability distribution, which is going to be the excitations of quasi-particles according to a calculation that was done several years ago in the quantum Boltzmann flow of the prime function approach, using essentially by the work of, I mean, I actually am a little bit unfair here. It says Saremba Nukumi that this was well understood much earlier by Pogulov, and Kadanov and Bayev. So this is something that people have, the physicists have been looking into that for years. So the model is a model of non-local interaction operators, generated kinetic type models of description of a spectral energy transfer dynamics of probability densities associated to weakly nonlinear interactions of coping amplitudes of complex values of the evolution of quantum or fluid systems. I mean, it's the quantum operators or quantum wave function, if you wish, and the fluid system, where the spectral energy states are given by dispersion relations associated to underlying model. So in a way, what you will see is that it's really a system that is completely coupled, and whether you have a stable configuration for that. I should say that the model comes and everything, it has been extenuatingly studied in after they did the first experiments of the quantum condensates. Then immediately a Nobel Prize was actually awarded in early 2000 for that particular group, and there was a lot of activity. And it's all about the model, but never was a discussion on whether the model has any well-postness. I mean, does it admit a solution? Does it admit a solution that is a state, right? And that is exactly what the discussion is about. So I got this from the book of, this is a fantastic book that described the model of Griffin, Nukumi, and Saremba, 2009. And they actually put this chart of physics, if you wish, that the stats, I mean, which is kinetic and quantum, right? I mean, Schrödinger was asked, what is the most influential scientist of the 19th century? And he said, Darwin and Boltzmann, because it defines a concept of understanding a fluid at the statistical level and in the concept of thermodynamics for gases. So indeed, the chart starts with Boltzmann, and it goes into this equation of the degenerate quantum states, but in the meantime, there were a lot of methods that linked Boltzmann to hydrodynamic and ended up into some model of kinetic equations for Bose-Einstein condensate derived by two fluid equations, of Kirkpatrick and Dorfman in 85. But if you think the path I'm doing is not this one, it's this one here, okay? And that path is much more modern, and it's a little bit more cumbersome because this is a single equation. All of this is you pass from one model to another by discussing a scalar model. But what it brings into here, which is really interesting, is this two-step, all right, on which they actually propose a coupling of the Gross-Pitayevsky equation to the Bose-Einstein condensation and the theory of gases of Pogulov. Okay, so how do you get into this system? So the system is the following: you are going to, in a Pogulov PLF separation and set of quantum mean field theory. What you do here is you split the quantum field operators, I refer to as phi, as a part that corresponds to the condensed gas versus the distribution of the operator that is in the non-condensed part. So I'm going to say this is the condensed part is in blue, and purple is the part that is in a gaseous state. But they are interactive, right? The interaction, I will go into the details later on, and it's very complex how to get there. I mean, you have to have several answers. Is that the expectation of the uncondensed part or the gaseous part has to be 0, and the density of the non-condensed part is actually the creation and annihilation operators combined together to have to get the condensation as a space and time function. However, the density of the gaseous part, the density of the condensate, it would be exactly the expectation that you call the spectral or the quantum density associated to the wave function. All right, but you have to add them both, and they are going to be interactive. And how do they interact? And this is the contribution of Bialet. Okay, and that dates to 60 years ago. So what they do is you pick up actually the Schrödinger equation. If you cut it, I mean, there are some people that may understand something here, but if you actually eliminate from this equation the purple part, then you get the classical Gross-Pitayevsky equation, because you may assume, for instance, that if the density is phi squared, you put it up here, you have this cubic instability that produces the condensation, which comes with the rise. Okay, but what they said, there is symmetry breaking in the quantum systems, and that symmetry breaking is, in fact, by this kind of regime on which you have the gaseous part that is going to be interacting with the condensate. And so that gaseous part, you model it, and the way you model this is it's called the Green's formalism. It's related to the Feynman diagram stuff of how you do these interactions. And what I'm selecting here, I'm following the Saremba oncoming briefing, is the lowest order perturbation. I mean, of course, you can do much higher perturbations. That is not included in the model. And so when you actually look at this perturbation, and these I's are really complex value functions, so it has these solutions have real and imaginary part, you have to actually couple to that to something that ends up being a real value object that is going to be a probability distribution function of the gaseous state. So what you want to do is to calculate the density of the gaseous state and the density of the condensate, and that sum has to be positive, has to be conserved all the time if initially so. The question is, how do you get the system that has such a property? For me, that is one of the things that I found it the most surprising. Okay, so you go into these symmetry breaking operators that I will describe a little bit in detail. I mean, I will not in detail. I will not describe in detail. I will actually talk about how you get into the path. If you want to read details, you have to go to this physics books. So what is clear is that this equation you multiply by I phi, and that reduces to the Madelung after the Madelung approximation. If you, for instance, would get out of the perturbation, then you get the Gross-Pitayevsky equations that gives you this fluid dynamics associated to amplitude and phase space, where the mean velocity is going to be the gradient of the phase. I mean, that's noted, but it's not exactly what we need here. Okay, we are not going to use that. So on the other hand, I want to bring to your attention how is this kinetic equation formed, or the equation that corresponds to the gaseous part. The equation for the gaseous part actually comes, and let me focus maybe in this little picture first, which basically gives you an explanation of how this system works, right? We are used to look at any conservative system, right, that has conservation of mass, momentum, and energy, and it's classical. This is a billiard, and these are elastic interactions. And then you know that in the gaseous state, you have two particles interacting and exiting the interaction in such a way that they have some conservation law associated with it. For instance, Boltzmann said it has to be center of mass and local energies. Here is not. Here you have two particles. This is actually very low temperature. It's not zero, but it's a transitional temperature when you are actually allowing particles to exit the condensate and interact with two ones that are coming, or particles that are coming, they collide and one gets trapped by the condensate because it gets very cooled down, but the other one is exiting. So we are going to be modeling what is called 2-to-1 interaction. That breaks conservation of mass immediately. Okay? I mean, it's no way out, but it conserves the conservation of mass of the probability density of the gaseous part. But if you add it to the condensate, it should remain that all of that is preserved. That the system, I mean, if it is closed on whatever or isolated, that should happen. And that's exactly what they model here. So in principle, you can start the modeling, and that's what it was done by the original work using the Boltzmann-Norheim equation, which is the one that's a quartic equation for bosons, which has the Bose-Einstein distribution at the kernel. And so you put this part here, and then the correction that it comes at the next level, which is this interaction. So the Norheim equation is quartic, and because you have the way the particles are interacting in order to get the Bose-Einstein distribution in the kernel, but it's a 2-into-2 interaction. But this 2-into-1 is what we put up here. And this 2-into-1, it has to reflect what we had here before. That if the Gross-Pitayevsky is perturbed at this level or with this thing, this actually has to be what you come up here. In a way that when you take the sum, and that should come here with a minus sign, you get a compensation of the two. And that was identified by Bogolov and Bialev, and it was reinforced. It's a lot of work of Kadenoff and Bayam and Kadenoff with several collaborators. So you know, in addition to that, you have to put here an advection potential that comes up from the classical Hamiltonian dynamics associated to the particle, you know, the probability distribution. And that actually that potential should include a self-consistent Hartree-Fock dynamic mean field, which it has the part of the condensation coming from the Gross-Pitayevsky, from the density of the condensed part. This is exactly what we have here. You see, it's an external potential, but here is where you get to see the coupling. So that is one component of the coupling. The second component, okay, or the other comment is that the condensate probability distribution that comes from this system evolves from the post-nucleation condensate for regimes that are above a T star. And T star is a finite time blow up that happens in the North Boltzmann equation because, as we all know, the Bose-Einstein condensation, Bose-Einstein distribution has a blow up at the origin. It's not a Gaussian, it has a tail like a Gaussian. But at the origin, it becomes infinite. So you may actually do a theory on which you have something on which the Bose-Einstein condensation, I mean, I'm saying point-wise, right? But what we are actually seeing that the part that actually corresponds to the Q22 is actually vanishes when you have a temperature for which you are in the very low regime that corresponds to condensate or becomes lower of it. And then we disregard. All right. In fact, what this is saying, it's going to change the way you do the dispersion relation associated to the local energy. So from a link from the semi-classical, so how do you get to do this kinetic equation? I just wanted to add a few slides because I know this is, there is a clear link between quantum mechanics and statistical mechanics, and that comes from the Wigner theory. And the Wigner theory really matters because it provides the framework to pass from one place to another. And so you start from the quasi-particles associated to the non-condensed part, sorry, it's there, and the calculation of the quasi-particle spectrums at low temperature actually is, and this is the formalism that comes from the Kadanoff and Bayer, it mixes the P momentum and the spectral in P in momentum and time omega spectral frequencies through the sort of breaking of symmetry, if you wish, or perturbation term or something that is given by the, or that's what the breaking of symmetry calls for, but the Wigner transform in a space-time, okay? And so if you do that, then you have to specify what are going to be these particular components of this matrix, and they are tied up, the atomic probability distribution and the quasi-particle distribution, right? And that comes all from the Kadanoff-Bayer formalism. They are tied up by these constitutive relations, okay? On which says that these quantities that appear here are spectral densities. They are the difference of the two that you have to be looking at, and that comes from the symmetry breaking answer on how you wrote the operators, the three operators that were. I mean, it's tons of pages, okay? I'm just extracting a few things. So then you do the, in the Golow Popov approximation, what you want is to do two things, is you want to describe how they're going to be these quantities based on functions that depend on it's called the coherent factors, which are you call it V and U, which are obtained from the non-local collisional forms that come from the energy transfer in the symmetry breaking. And they're viewed as a dissipative effect into the quantum system. And so in that setting, let me say that these functions here are determined by these factors that appear A1, A2, A3, which are going to be related to the sort of metrics of transitions that defines this passage of breaking of symmetry. So I have to describe for you what are these numbers. And that matters because that is the most important link in the calculation, okay? As much as for the stability. And that if you look at those things, these are modeled, right, as precisely the wave transitions in frequency that come from the Madelung interpretation, from the Madelung representation, the velocity of the Madelung representations, and in terms of the quasi-spectral energy, that is going to matter because it's the energy that corresponds to the gaseous part of the system, all right? And so from that, what you get is then that it gives you, so you take this and answer, and you do the calculation, and from here, this is actually not hard to compute, but you get that the coherent factors satisfy these relations. Well, this is fine because this is actually all happening at the gaseous part. It's the energy and the energy there of the momentum, the classical kinetic energy of the momentum. But the product of the two picks up the condensation of the, so the density of the condensed part. So all of a sudden, the exchange of states, right, under certain ansatz on which you have, you know, that the variations of the harmonic part of and of the condensed part of the condensed density is very small. So you get that you end up with a system that has very neglected variations in space. This is something that quantum mechanics, I guess is forced to do to come up with some clue. I'm not saying that someone after that can actually solve the same system with the space, all right, with suitable boundary conditions. But under that answer, what you get is that the spectral energy, and this is what is going to go into the kinetic equation, is proportional to the classical kinetic energy momentum for the gaseous part, plus something that depends on the condensed part, on the density of the condensed part. So when you put this inside an integration with respect to P, this is blind, and you can pull it out. And then you said the next answer. So now you can write the equation. The G function is important because you get the S scattering wave. And so there is a memory of quantum mechanics may have been still affecting the system. So then, but you get at least this coupled quantum kinetic model. And what is interesting is that these operators are given by these three fractions on which you have, and each of them is described, and that is according to Feynman diagrams that you calculate them, right? Or the green formalism. Everybody, have different ways to come up with it. But it has a transition probability where that transition probability, right, is going to be the product of the dispersion relations, and the dispersion relations, I just said, is what we call it, or the particle energy is WP, and the dispersion relation is the fact that you put this singular measure associated to what is the law to be with respect to energies. Okay, so this is this comes up on a system that is going to conserve momentum and is going to conserve the energy, but not the mass, until you couple it, the mass, with the mass of the condensate. Right? So the kinetic equation, I said, whatever is in P, you can talk about energies at that level, right? For the condensed part, the contribution comes into affecting how is the transfer of a spectral energy, because this law involves this time. And then you said, well, in the case in which it's very cold, then we are in a regime where this order with this term, which is quartic, is much lower order, because you're going to be in regimes where P is smaller than 1. I mean, the magnitude of P is smaller than 1. So the quartic term goes away and you really get into quantum effects. And so the Boltzmann-Norheim and the classical Bose-Einstein quantum model is gone. It's irrelevant, okay, in this regime. So, okay, so then what we have, clearly the masses cannot be conserved, but what we get here, oh, sorry, this Q is extra, that should not be there, is the coupled system that corresponds to having the condensation after you average in space. The condensation, or the density of the condensed part, is the evolution it gives by the breaking of symmetry, something which is proportional to this 2-to-1 operator. Okay, and the kinetic equation has the same operator without the, so let me just take this out. And it gets the same operator with the opposite sign. So when you add them up, I mean, when you average this equation with respect to space and add them up, then you get the system that is that is conservative for this. And it's interesting that when you look at the condensed, when you look at this, so M0 here is the mass. Actually, I'm going to call it later on M2. But in any case, what you get to see that this quantity is constant in R space for any external, and it becomes constant for any potential. So that means that for any potential, external potential, this is going to be a constant. Okay. So the theorem is, or the statement, is that system admits an existing and uniqueness theory for a well-prepared solution for this pair. And that solution persists. So in a sense, right? I mean, I just stated the system, the statement here, and it says the following: we are going to construct solutions that have, that are going to be continuous in time. So that's actually important, because you have you have a model and you want to understand all of this carefully. So it's going to be continuous in time, differentiable in time if you enlarge the space. But if not, if you want it to be just continuous in time, you get into a space that actually is going to be a subset which allow us to do a contraction mapping theorem. And that it really matters. Okay? I mean, the contraction mapping theorem is like Newton's iteration. You start with an initial data that is nearby something nonlinear, and you can secure that you have a convergence to a state for all times. Okay? For all times. It's not that you do it at infinite, it's just for all time. So, okay, so I just, and the set here is, all right, what you have to have is you solve it in a set of positive functions. We have mass, finite energy is this, and they need at least 6 more moments. I mean, this 8 and 6 is a technical discussion, and the solution can blow up at the origin, but when multiplied by x squared or p squared, then it's rounded. So the blow up can be not bigger than 1 over x squared. It's an interesting result, and I like to recall Carlo Cercino says the present contribution is a step forward of the solution, and you can read it in light how you update this for semi-classical quantum dynamics. But in the classical setting, Cerciniani said, step forward to the solution of extended kinetic theory defined by truths de la Muncaster to discover and specify the circumstances that give rise to solutions that persist forever. And this is an example of it. Okay. So I don't want to spend much time into this thing because it may be exhausting for the audience, and this is really mathematics, and I want to show some of the numerics, but then you get a flavor that there were many things that came into the game. One is that the dispersion relation or the excitation energy, as people like to call it, was reduced into something that is just because this term went out, you are in a very cold state, and in such a cold state, you have a quantity C that actually depends on the condensation of the density, the condensed part of the density of the condensed part proportional to the G function, to the scattering function, the normalized scattering function by the Planck constant and the electron mass. So if you are going to do numerics, you have everything there to scale down and to get into the right numerical frame. On the other hand, what really matters is the transition probability. Also have these 2 terms coming up here. And then you can, in order to study this equation, what we did was the following. All right, we have to solve to find a solution to this coupled system. So we rescale the momentum space. And in that rescaling, you get here this constant that depends on the G, but that actually you can transfer here to rescale in time, because the leftover that you get, actually, this part is actually what is going to make the system work, the division on the rescaling for 1 over n. And now the kinetic equation is free. It's in P tilde is free of the condensation. And then we can work it out in the classical way, or at least the manipulation that we do to write the existence here. And indeed, we can make it work. It's important to recognize that this has a positive contribution and a negative contribution with a collision frequency. This is kinetic theory, classical. And then identify, this is something I was showing Jose, that even though you don't have this classical form of Boltzmann that now we understand very well how you manipulate it. It has a component that the negative contribution, which is the collision frequency, has to have a bound from below. And that means it has coerciveness. And coerciveness means stability. And if you lose that property, you have no way to succeed into getting a global in time solution. And so with that property, we study carefully how to get them up. And then, so here is all the details of the study, and I can leave the details of the lecture as much as many of the things of it has a quantum H theorem. This is actually interesting that the quantum H theorem also have the Q12 operator, the Bose-Einstein distribution in its kernel. And you have a particular scaling that is due to the operator. How is that the density and the mass are going to connect to the initial, at infinite, to the initial densities that come up from the relationship of the condensation. So that is basically the result. One of the things I want to say from the mathematical point of view, and this is really probability, is you are solving these problems of probability distribution. That means you have to deal, this is not L2 theory, Sobolev space, Hilbert spaces, like everyone likes to do operator theory in physics. This is integral functions with moments, which is to look at the expectations at any order, right? And you have to, because there's no way that you can start with the Boltzmann equation to do anything in a Sobolev space or in an L2 space. That will not be. L2 estimates on the Boltzmann equation only come after you understand the L1 norm with polynomials, but that is exactly what it means to be a probability distribution. Right? You have to do it that way. And so, in fact, what we have is that this coerciveness statement allows me to look for any moment of any order at the variation and get in control, but something which is decay, right, with a much higher moment. So, and that means that you can do interpolation, and that gives an evolution for the K moment to be of order, right, of this quantity that has a negative term with a superlinear power. And a superlinear power, an ODE, which has a positive part, right, with the same unknown. And then you subtract the same unknown with a superlinear power has global in time solutions. It propagates the regularity. So if you have a K moment bounded, it would persist forever. But if you have even a K moment above 8 here or above 6, it will generate all moments. And in fact, it's not only that, it will actually get that all moments are summable. So you do have a control of the decay rate of the case. And that is why it works so nice. So you can actually get this, you start with it's like the heat equation, right? You put an initial data that is discontinuous, instantaneously in time gives you infinite derivatives. Here you start with 6 moments, instantaneously in time, you generated all the moments and even the tails. It's like it flattens the distribution very quickly. And that is something we know it happens for the Boltzmann equation. I did a lot of work in that. So with that, let me just say that this is a little bit more, it's in detail. The statement of the theorem comes up how the solution has to be well prepared, and that requires a particular identification of this term delta, which has to be a number, which we calculated here to be smaller than this expression. And that, this is the casual operator. It has to be smaller than this expression. And here is where we need that our solution initial data, if it has a blow up, it's okay, but cannot be worse than 1 over x squared. Yeah. So someone can remove that condition either. But the delta has to be something that is strictly smaller than that. And so with that, we get to solve this causal operator, which is an operator with memory, and then we have a fixed point map algorithm. Okay, and that actually a fixed point map can be programmable. So from that on, I put some conditions, and we have a way to identify theorems. Now the kinetic theory on which you have an operator that satisfies these three conditions, it's enough to have a system. All right, and so here is the result on the tail, and that was it's interesting to see that you start with 6 moments and you generate tail decay. That is something. It's a phenomena of Hart potential, and in fact, this is the consequence that the transition probability was cubic in the energy spectrum. Right? It was this form, or what is the collision frequency. So from that. So what I wanted to say about the numerics is a different problem. Okay, and this is a problem on the tokamak and how you get particles to be, again, the same thing, right? You are exiting the area or where the plasma is confined, and you start to have interactions in between the particles. And those particles should be actually interacting with the corresponding spectral energy wave growth rate that you have coming from the plasma. I mean, or modeling, it would be somehow like looking at the dispersion relation associated to the Maxwell's equation for highly magnetized event. And again, that gives you a system that ends up coupling, right, the momentum that you need for modeling the quasi-linear diffusion in a plasma with the spectral wave variable that corresponds to the dispersion relation of the plasma wave induced by the Maxwell's equation. So can you actually do this calculation? And the physics again has been is in the work of Sticks, in the book of Sticks, very well explained. Many people have worked, but there has not been a simulation done yet. And this is something we did about a month ago with one of my students in ICE. And what you have here is a coupled system. Again, it's a diffusive equation now. It's not a kinetic, it's a kinetic equation because the probability density, but it's in divergence form. It's like, imagine a Fokker-Planck type of equation, except that here is pure diffusion. That's how they model. And you can cut this from random walk without deviations and so on, except that the coefficient in the diffusion, right, is going to be altered by this W here, which is the evolution of the wave function. And again, the physics, and this is work of the last 2 years by the group of DOE, we are doing a project on runaway electrons avoidance and mitigation. The fact is that here what you get is a coupled system on which or the coupling is the wave equation is independent on space, that kills the space. And they said, well, to explain it, we look at the space average system. Fine. You can always do that. You can just take integrals in space, assume periodic boundary conditions or whatever, which is in the tokamak, and that would actually give you, for the ODE, the following, that if you have a strong magnetic field, then you have a source term, and this is the perturbation of the spectral energy wave. And then with that, you actually couple the spectral energy wave, right, in the following sense too. And this is going to be, it's a little bit elaborate, but it works wonderfully. You start with an initial data, right, for the distribution as much as for W. You calculate first for that equation, this gamma. That gamma is an integration that is going to involve derivatives, whatever is inside the divergence of the diffusion equation. And that depends on F, which depends on the variable P. But you have a dispersion relation that ties up the spectral variable K, which is the one that corresponds to the wave, through P, in this relationship, which is inversely proportional because you have exactly as you have it in quantum mechanics. when you do the modeling, right? And so what matters here is that if you look at this expression here, it should be a function that depends on the spectral variable. That means that this integral averages on P, and that induces to look at F in 1 over K. That means the frequency over K, right? Can you calculate that? Yes, you can calculate that. And in fact, we are doing the theory now. You get an extension of Hamilton-Jacobi equations. It's really extraordinary, okay? And then what happens with that when once you have W, you can calculate the diffusions by the similar process, but now you integrate in K because the diffusion depends on P. And all of that is tied up by a factor U that appears in all of them. And that factor U, no one has a name for it. They just put it there, but it's and the factor that mixes the spectral energy and momentum coordinates through the dispersion relation and the resonance condition. So in a sense, you get a little bit of what happened at the quantum level system, in a sense. I should say that, let me show you. Oh, I see. I think I forgot the resonance. Everything then is, everything else is combined with the fact that what is the dispersion relation that we want to put here? W. We said, well, you can get it from the plasma physics. Usually it may be an answer, and it says it could be the plasma frequency mode, or could be the Whistler wave frequency mode. And that would be a choice that different choices, you know, momentum that may be very high or very low. Which in fact, what happens is that you can calculate the dispersion energy by looking at the polarization metric and looking at the zero of that polarization metric. Because this is a quadratic form, we realize using MATLAB, this is the numerator of the determination metrics, and we were able to calculate exactly what are these numbers. And then we did a simulation on which we actually calculate the dispersion relation exact, in an exact form, and it's this orange surface which is here. It's trapped by the plasma wave and the Whistler wave at different ranges of P or energy. So it's very interesting because you can trace down, and this is what we did numerically. So here is the iteration, and this is my last slide. Wow, they have a couple comments. The iterations is a iteration flow, and I think this is a basic. It's really a basic template to do mean field theory calculations. Okay, in the following sense, we are here. I don't have a theorem of a stationary thing, but we have a solution that stabilizes. So I think I'm going to have it here because we are seeing that this iteration produces something that eventually stops. It's like it's almost, and it has been described in a Russian paper of 65, that is like a self-similar solution which eventually converges to a stationary state. Well, I mean, we are in the search, and I think we have some work that we are planning to do. But the iteration that I have in this flow chart is you start with an initial data, and you see here with this initial data you need to compute omega and then W, and from this initial data you need to compute the first diffusion, and then you solve for the next step, and then they go again here and they go again here, and you go into the next step. And actually what we show is that this system also that we have calculated, and don't have the thing to show you, that the mass of the PDF and the mass of W of the wave equation, you add them and they are conserved as much as the momentum and as well as the particle energy, which is here is the blue is the energy of the particle, decays a little bit. Here is the energy of the wave function, which increases, but the sum of the two actually is constant. So the scheme is conservative, and that is important. Here you see the evolution of the PDF And that gives you this blob that is in. And here you see the evolution of the diffusion. So this is the initial diffusion, and it actually starts to confine it, to confine it, and that confinement actually localizes it into a surface and seems to stop diffusing. And last, this is the evolution of the spectral energy. And while this seems is dissipating, is that here you have very high values, here are lowering, and so at the beginning have some effects, but then they start to stabilize and everything comes to it. There is an H theorem, and an H theorem explains stabilization as well, and explains that maybe you can actually get a good mathematical result in the background. And the basis functions, we did this with a specific scheme on Galerkin approach, because it's anything that is kinetic theory, it's very amicable to do Galerkin methods or spectral methods. And the reason is they may be more efficient than Monte Carlo nowadays, and spectral methods as much as Galerkin methods rely on weak formulations. It's like taking expectations on the basis, and that actually tends to be very, very good. And so I thank you very much for your attention. Thank you.
Thank you very much for the very interesting results on the process of the quantum problem. So something that caught my attention is that you have essentially two inequalities, one in the classical problem and the other in the quantum, which are basically like some sort of analogs of the Shannon symmetries. For the quantum problem, do you think that model might satisfy another entropy inequality, or that there might be another entropy?
Actually, that's interesting. We do have an entropy inequality for the quantum kinetic system, and that gives you the relationship on how you tied up the two condensations at infinite with the initial data. So there is a relationship of how the two how the evolution of the condensed part, the density of the condensed part, and the density of the PDF actually have to coincide, take a shape by the calculation of the fact that you have this entropy that takes to the kinetic quantum system, or quantum kinetic system. What we don't have yet is the decay rate, but I think we can work. This is work with Ricardo Alonso, which is a former student of mine, and for the quantum kinetic part, and Minh Tran, that they are he's in SMU, and this latest part is with Kong Wang, which is a CSEM student in ICES, and Michael J. Hayduck. And I'm trying to get Jose involved in the numerics of the quantum, in the quantum kinetic system, because I think it's a very, it's doable. Yeah.
So this is very interesting. I'm not sure if I may appreciate how you're bridging gap classical gasoline gas here, making the alternate route. But I'm curious, what kind of different results do you get taking this different route? And do you get a different expectation or define a wave function? Do you see different rates of condensate formation? Or is it just that you have now analogies to these other types of condensates that are using non-quantum structure?
That's very interesting, because the result that we get to see, right? I mean, you have here something that is going to, so on one hand, we have that the kinetic equation is going to go to the Bose-Einstein shape, but the temperature of the shape, and this is a relationship, affects how is the relation on how the density will have to converge. So somehow what we don't know is that the condensed part, the density of the condensed part, where is it going to lay down? And that is going to be different than the density of cross Abms alone. Because the density of group is converges to 0 or 1, because you have this double, well, things very trivial, or the quintic equation, the roots of the equation. But here you can get states that are different, that are going to depend, right? Or they will be, by the way, the density of the condensate is going to be a number, but it's going to depend on the average of the, it's going to depend on the mass of the Bose-Einstein distribution for a temperature that comes from the scale that you did for the right? And the rate of decay is going to depend on this G constant of the scattering.
Dan Sanford prepared a study cavity experiment showing the evaporation number within 5 atoms as it's going down of gas ensemble. I wonder if it has statistics.
That would be, I would love.
Yeah, I just saw it.
So send me whatever is written, even if it is handwritten.
Dan Sanford.
Right. Send me a picture from the
I
photo.
almost picked the
Okay. Yeah, but I that's what I would expect, because there are actually this.
Yeah.
And it's revisiting a little bit how things really you should look in this direction. And I found very inspiring the panel, the comments that you did, kind of, because I think this is what needs to be done and said. And it's going to be small increments in small steps. I mean, from Van Roosbroek, when he did the first semiconductor 67 years ago, he didn't dream we would be seeing each other on iPhones and moving with devices that had billions of what he had to do. And that's like that. That's so, this is the beginning, not the end. Thank you.
So, Dr. Gambler, we do have a question from the audience,
Yes.
from our remote audience.
Oh. Well, I wish I could answer that question. I'm going to defer that question to either the two previous, to Tyler or to I forgot your first name. It was Chris. Because I'm a little bit too tempted to say it. I don't know what are the technologies right now to do quantum confinement. What we seems to be saying here, perhaps, is that the quantum, so the model that I have, it involves a confined system because it's completely isolated from the exterior impact. So we are saying is in an isolated system, you are going to get densities that may be convergent to different states than the quantum system alone. That's basically what we are saying. All right. Okay. Thank you. Thank you very much. Okay. All right.
Hi, and welcome to our last panel. This is on the convergence of quantum computing and AI. So we all know of the economic importance, industrial importance of AI, and it's becoming clear that there are at least potentially problems that quantum computing can address significantly faster than classical computers. So the natural question that comes from that is, can you use quantum computers to solve AI problems? So with that, I'd like to start off by having everyone introduce themselves on the panel. Jose, you can go first. I don't see the other panelists, so okay, there they are.
Thank you, Tyler. Well, hello, everybody. My name is Jose Morales. I am an assistant professor at the Math and Physics departments of the University of Texas at San Antonio. Regarding my lines of research, as a PhD student, I work on numerical methods for electron transport in semiconductors, where I use the kinetic theory framework. It is a very useful framework because you can go between the macroscopic and microscopic scales passing through quantum. And some of the versions of the numerical methods that I used were discontinuous Galerkin. Then I did a couple postdocs at Vienna and McMaster in Canada, where in the first one I dealt with stochastic methods for those types of basically collisional and diffusive electron transport. And in McMaster, I dealt with essentially optimization problems or inverse modeling in lithium-ion batteries for non-equilibrium processes. And the techniques that I used at that time were essentially multi-objective optimization and Bayesian estimation. Now, as an assistant professor, I have a research group where I work in quantum semi-classical problems, and they go into two research line directions. The first one is essentially to study the electron transport in semiconductor problem at the quantum scale, making use of this kinetic framework, where we can go from the mesoscopic to the quantum scale. And the other one is basically to study quantum information from the kinetic theory point of view by studying open quantum systems, which is basically a noisy quantum channel where you have a system and an environment, and then there is an influence by means of a diffusion operator, and you can look at it by means of either a Wigner description or a density matrix one. So as basically to the topic of quantum computing and artificial intelligence, I am a newcomer of the topic, but I'm eager to participate and basically perform an extensive literature review to basically get acquainted with this very interesting topic.
Tammy Borders, would you like to introduce yourself?
Sure. Tammy Borders, business development for Honeywell Quantum Systems, and just recently joined Honeywell. My prior job was technical advisor for Next Gen AI for the Department of Energy, NNSA, Defense Nuclear Nonproliferation R&D. Got to see a lot of interesting work there, particularly with challenges associated with commercial off-the-shelf technologies. My academic and industrial background too is largely, while it's a PhD in chemistry, focused in the area of machine learning and physics-based frameworks for complex materials.
Cool. Megan, would you like to introduce yourself?
Yeah, hi, I'm Megan Cohagen, and I am a quantum computing applications engineer for Honeywell Quantum Solutions. My background's actually in operations research and mathematics, so it's been an interesting journey coming to quantum computing from outside of the physics community, and kind of just bringing a different perspective there in terms of, you know, what exists today with traditional optimization methodologies and classical approaches to machine learning, and how does that tie into quantum computing and what that looks like in terms of quantum advantage and estimated timelines. And so that's been a pretty fun journey to get to go on, and where I'm at right now.
And so we have a replacement on the panel. Rafal is being replaced by Paul Finlay. So Paul, could you please introduce yourself?
Sure, thanks a lot. Yeah, my name is Paul Finlay. I work at Xanadu Quantum Technologies. We're a startup out of Toronto working on building quantum hardware as well as quantum software, including quantum machine learning software, open sourced, of course, for everybody to use. It's called Penny Lane. My background is also in physics, actually experimental nuclear physics. But after leaving academia, I moved into AI and machine learning. And actually, before I joined Xanadu, I was director of data science at Royal Bank of Canada, working on a number of machine learning AI applications.
Thank you. So just to sort of jump in, the first question I wanted to ask is bias questions, one of the things I'm most interested in. There are a number of well-known AI applications for quantum computing, but you can kind of divide them into two categories. Those that take a machine learning problem that's like that we use classical computers for and say, all right, well, we're going to use a linear algebra package, a quantum computing linear algebra package. We're going to do this this algorithm that's basically the quantum equivalent of a classical AI algorithm, but faster in some way.
And the other is more geared towards NISC devices and focuses more on hardware and says, all right, well, this is what we can make in the near future. And what sorts of optimizations or AI type problems can we attack starting from that rather than just going, all right, well, this is a neural network and let's make it quantum. We go, all right, well, let's see what sort of optimization problems we can attack using what we have right now. I mean, I'm curious what the panel thinks the importance of those two directions are, whether they're both equally important to focus on, what directions they think is most promising for their individual institutions, and just give your thoughts on this. Jose, you can.
Yeah, sure. Well, basically, the two approaches sound interesting from the point of view that, well, you kind of start with the quantum hardware in mind and then try to basically come up with algorithms based on that architecture that would be useful, though that's personally from a point of view, a little bit of a longer, basically a longer term approach. Whereas if you basically try to, well, with the knowledge of a classical algorithm and to basically do the quantum implementation, a good part of the problem has been tackled algorithmically. So the question is basically to come up with the quantum extension of this, and so that part is solved. And perhaps from that point of view, might be shorter term, but yeah, that's my take.
Megan, I believe this is your kind of area of expertise, so would you like to weigh in?
Sure, yeah. I would say the short answer is I think both are important. I think that looking at some of the theoretical guarantees and the speedups has led and highly motivated us to try to build quantum computers. On the other hand, we have these NISC devices that are noisy, and so the question is, what can we do with those today? And in terms of the quantum algorithms, there's kind of that, you can create a quantum algorithm that's geared more towards using all the advantages of a quantum computer and its unique capabilities, and then and try to go that route. And you can also, kind of like you were saying, try to create the quantum analog of a classical algorithm, such as a neural network, or there's been some really good things with quantum kernel methods. And so so I see fruitful sort of scientific discovery coming out of both of those. And I think there's still so much research to be done in terms of, what are those first real, practical applications going to be. I think we've got kind of some strong hunches, but in terms of right now, I think the field's sort of open and there's so much work going on. That's pretty exciting and fun as well.
Thank you. Could you since this is sort of your area, could you elaborate on some of the types of problems that we know about that NISC devices could potentially help solve? Like what I feel like for one of them, it's like, well, we know what neural networks are used for, but for the more hardware specific problems, the set of problems they can address is a little bit smaller. Could you speak to a little bit to those problems and their what they can be used for?
Right. Yeah, I think without a doubt, and partly what motivated us building quantum computers is being able to model inherently quantum problems. And so you think of simulation of quantum many-body systems where we're limited in our approximations classically. Those have very high promising quantum advantage, and so as the Honeywell team kind of done work there in terms of the algorithms, such as our holoquads algorithm, really pressing in on that direction. And then in terms of outside of that, when we think about machine learning and optimization, we've got pretty good classical techniques and that they perform well. And so if we're trying to really kind of tease out what the advantage is. You know, is it coming from the performance? Is it coming from the accuracy of the models? And so I think there's pretty good evidence that there's, you know, maybe some hard to sample from probability distributions, for example, or, you know, kind of this quantum kernel idea that, you know, may be promising on NISQ devices. I think the question would be, are there any such probability distributions and whatnot that people in the classical ML and optimization world care about that aren't just related to quantum distributions and quantum systems? So I think there's kind of multiple things going on there.
Great, thank you. Paul, do you care to speak to this question?
Yeah, sure. It's tough. So many good things have already been said. Maybe I'll be a little bit controversial and say neither of these approaches are super interesting. I think what would be really you know, important to do going forward as well is to look at the fundamental building blocks of quantum machine learning and see if these are the right building blocks. So, you know, just copying quantum, you know, neural networks, or rather classical neural networks, and making a quantum one, and just using quantum gates and training them, you know, trainable circuits is a sort of a given. But are those the right ways to build quantum machine learning applications? A lot of work hasn't been done in that area. We've just kind of assumed and copy that over. So I'd almost would like to see maybe an approach of stepping a bit back and looking at the fundamentals, and maybe starting to treat quantum machine learning as its own field, to see what these differences are and how they could be important, is something that I think, again, trying to be controversial for the panel, I'll throw that out there as something that's important to do.
So could you speak a little bit more, like the beginnings of my understanding of the beginnings of neural networks and that sort of thing? It's not as if someone like started with, you know, what is the fundamental thing we can make machine learning out of with a classical computer? So it was more like not correct idea of how the brain works. So what would going back and looking at the roots of quantum machine learning look like?
Yeah, that's a good question. The quantum side is not where my expertise lies, but just talking with my colleagues about these problems, that's basically what they suggest. You know, you're right, like the originally classical machine learning with neural networks isn't looking at aspects of the hardware for doing it, although there are ideas behind like the neuromorphic computing, you know, representing the brain in hardware that has also tried to do machine learning and AI that way. But the idea with quantum computing, though, is that so much of the power really is in the hardware itself. And so taking that step back and thinking, can we model the problem using the hardware maybe in such a way that it does give a certain advantage to the quantum machine learning, the trainable problem, as opposed to just, you know, taking some variational circuit, training it like we would do for a classical algorithm, and seeing what we do there, almost like a how to say, like a rethinking a bit of the building blocks for that.
Cool. Yeah, I'm all for rethinking building blocks. Tammy, would you like to speak to this?
Sure. Very quickly, I follow up, and I'd +1 to what Paul said as well. So what I always like to do is start with the end in mind. And so with my last role, working under the Next Gen AI portfolio, what we did was focused on challenges where commercial off-the-shelf methods fell short for specific security challenges. And this included things like complex noisy environments, sparse data, rare events. How do we drive robust deployment and decision support instead of just single one-off type models? How do we address weak signals? How do we classify weak signals? How do we address deception? How do we address bias? So rather than coming at it from the perspective of near-term or long-term, like Paul said, come at it from what are the challenges today? How can we define the challenges and then define use cases where we can make an impact based on the needs of the industry and the mission?
So could you give some examples of the types of challenges that y'all have identified?
Sparse data is an easy one. So lots of times we also develop these myths. So one of the things people came up with, my data is great, my model's great, I just need more data. But in many cases, you don't get more data. So your model has to work with the data that you have. So how do you deal with sparse data? This is actually an area where I believe quantum will have an advantage. Rare events, an example in finance, well, you have example in finance industry, fraud, right? So how do you detect rare events? I believe they use autoencoders today, pretty successful. Well, successful is a strong word, but and one that I would really love to hope that quantum can tackle is responsible AI, so bias. In particular, you know, we have data sets which may not, is it the data set? Are they not equally distributed, which is probably the case, or is it biasing towards one entity or another, et cetera? So can quantum make an impact in the areas where classical is definitely falling short?
So you say that you think that quantum would be better for sparse data problems. What are the reasons that you would say that?
GANs, yeah, generative adversarial networks. And so some initial studies, and Megan is the expert here, so I'll let her talk to that. But looking at the way that they can have multiple state representation. So when you're trying to generate data, I believe, well, from the literature and the publications on generative adversarial networks today, I believe quantum has a potential to do a better job with data distributions and generating more accurate representatives data sets when you were generating sparse data to augment the sparse data problem.
Megan, do you want to comment on that?
Yeah, I think that's, I think kind of where this idea is getting is, you know, when you're modeling the distributions of something, there not being as much of an issue with loading a bunch of data onto the quantum computer, which in some cases, you know, for some of the provable sort of speed ups that are out there, we're going to need those large fault tolerant quantum computers to do it, and some version of something called QRAM. And so, which is like a quantum memory. And people are starting to work on how to sort of implement that now, and what might that look like. But in terms of, you know, big data problems, I think that's probably going to be sort of a longer timeline, I guess. But if you think about what we can do with the quantum computers today in modeling hard to sample from distributions, I think that's where this sort of idea with the generative models comes into play.
Okay, thank you. So kind of just like branching off of that, the next question I had was of the known machine learning or optimization uses for quantum architectures. Obviously, the first ones that we're going to be using in industry are just almost by definition the ones that are the easiest to make, the hardware that's capable of doing them. I was curious what algorithms that we know of would you say are the ones that both have the quality of being a practical use for some industrial purpose and also being easy to implement on more near-term devices. Jose, do you want to?
Yeah, sure. Well, I can think of a couple of problems. First one is basically a problem of simulating molecules, not so big molecules. So the language is there in terms of quantum computing. The second problem may be just motivated by a recent paper, September of this year, basically related to the discrete logarithm problem, which I mean, it's a little bit theoretical, but has some connections with cryptography. And what they did was to essentially study Liu and some other co-authors this algorithm that combines quantum kernels with support vector machines. And so they're able to outperform classical algorithms that would only see a random pattern, or just seeing basically quantum version of the algorithm, they're able to solve the problem. And apparently they assume basically that the data transfer is only classical. So those are two problems that come to the tip of my mind.
Thank you. Megan, do you have any thoughts on this?
Yeah, I think certainly, I guess, and yeah, in terms of near-term applications, again, kind of around the simulation of quantum systems, I think we have pretty high confidence that's going to be one of the earliest applications. And maybe for its crossover to AI or optimization, like I think of something like matrix product states where that has strong physics ties, and maybe there's something there to explore in terms of tying it back to AI and ML, or as we kind of mentioned with the generative models or kernel methods, it's a little bit more unclear in terms of what the crossover times for some of those look like. So I think that's something to really figure out, so we know when that quantum advantage comes. But yeah, it's just there's so much happening right now, even just papers coming out in the last week, and so it's hard to kind of cross anything off the list at this point. But
yeah,
I definitely think we've got some good indicators.
Thank you. Paul, do you have any thoughts on this?
Yeah, I mean, I can definitely echo what Megan was saying about so much coming out so fast these days. It's hard to keep up. I can certainly speak to, I mean, our near-term device and what you can do with that. Our hardware takes advantage of a process called Gaussian boson sampling, which preferentially samples from dense regions of, if you think of your data represented as a graph. And so this is great for doing graph problems, max clique, trying to find densely connected subgraphs within a large graph, even things like the knapsack problem, right? Which is very, very important problem in like finance, where you're trying to pick a collection of stocks, for example, into a portfolio or something. So these are definitely, as we scale up our hardware in the next couple of years, these are the kind of problems I could see being sort of the first ones ported over to quantum.
Thank you. And Amy?
Sure. So the area I'm most interested in, based on my background too, is going to be materials and chemistry. And so there's a lot of opportunity with the VQE variational quantum eigensolver. I always have to look up those acronyms. But looking at things like unordered systems, things that are very highly correlated, where the bond, where the Warren-Oppenheimer approximation fails today, looking at transition states. I'm hopeful. I know there's a lot of work, but again, there's a lot that comes out every week. Something new has happened, and it's like, oh wow, that's going to enable this or that. So that's an area that I'm very excited about.
Thank you. Yeah, and I was just kind of more generally, especially since both of y'all are industry people, all three of y'all. What would you speculate would be the nearest term, like industrial use, or at least the category of an industrial use in trapped ion quantum computing? Would it be the same as what you just said, like simulating physical systems? Would it be, do you think there's room for analog quantum simulations, or do you see the first industrial uses being things that break things down into gates and do operations that way? Does anyone have any? Megan, do you have any thoughts on that?
Yeah, certainly. I think computational chemistry materials, I agree with Tammy on that, that kind of being like one of the key verticals where quantum computing is going to have an impact nearer term. And in terms of the Honeywell architecture, so I guess we've done work along these lines. I have a paper for an algorithm called HoloQuads that's on the archive. And in that, for example, our quantum computer has the ability to do mid-circuit measurement. And so we took a quantum circuit that would utilize 32 qubits, for example, and using mid-circuit measurement transformed it into a circuit that needs just 9 qubits, is able to, run a longer depth circuit. And so that's kind of, one of the areas I think where we've sort of focused. And our theory team has done a lot of good work.
Paul, do you have any comment on that?
I don't know a lot about the trapped ion systems, so I'm not sure exactly, what physical systems they'd be great at working with, but I generally would agree. It sounds like they'd be good for the chemistry applications.
Okay, thank you. One question I had, we kind of have, Honeywell's actually not this anymore. There's 3 broad categories of people that are working on quantum computing nowadays. There's academia, there are subcomponents of a larger company, and there are startups. And I was curious what your thoughts were on what the difference is in doing research working for those 3 categories of thing. Are the incentives different? Is it are the long-term goals different, and how does that affect how you go about doing the work that you do? Jose, do you have any?
Yeah, sure. Well, from my point of view, I can talk about the academic research. It is clearly of a longer term as opposed to business units or startups. Clearly, a large business unit will have a less shorter term, but the startup is the one that has the shortest one. And I mean, from parallel side, well, this has not to do exactly with quantum computing, but I worked on a couple industries or academic topics related to industry, which were semiconductors and lithium-ion batteries. And a large business unit can provide funding to academia to basically tackle longer research terms, but the mindset is perhaps shorter here. So that could be the analogy that I could foresee in this other topic.
Tammy, do you have any thoughts on this?
I do actually. I was thinking about that. That's a great question. Looking in academia, I agree. It's longer term. It's not only longer term R&D though, but this is where we're going to turn to define things like ecosystems. So, what are the one huge challenge with quantum computing, in my opinion, is workforce development. It's having written a lot of mathematical software and used it. One of the first things I always ask for is, where's the documentation? How am I going to get support? How can I learn about this? And so we all have scoured the web looking for things, but academia has the opportunity to come together and put together these larger collaborations or consortiums, which include things like workforce development. Start working with industry and saying, hey, we can do the technical part, but what we need to define is what are the use cases and the challenge spaces. And so that's going to be an involvement with pre-competitive work with industry and academia, which is what NSF and Department of Energy, I believe, have set up in the last couple of years or so. Startup-wise, that's another really good question. A lot of times they are near term. They need to make money now. They can be very focused. They can be very narrow. They have a specific thing they're doing. A lot of the startups I've worked with in the past, while they are somewhat narrow, they also look in high tech, they look to federal funds like Small Business Innovative Research. And so they want to get money in order to continue their research. But not only are they doing technical research, they're also looking at novel business models. I'm going to use Citrine Informatics as an example of how they really got materials informatics off the ground. It's a phenomenal company led by some great folks where they have used machine learning model and through an API where they're connecting databases to drive value add and have both freemium premium models. So they have both technology and business innovation to grow that company. Internal R&D of large companies, I'll use Lockheed as an example. They have an initiative called the 21st Century Warfighter. And so they have 12 big R&D initiatives, I believe. And each of those have geared towards what can we do with X, or AI, ML is one, that will then help our overarching company initiative. In many cases, working internally R&D in industry, you don't get to publish, having been there, and a lot of it stays internal. So that's a little bit harder, but you do work with startups and academia, et cetera, and small business too. But you do have to show how it adds value to the bottom line. Usually within 12 to, well, it depends on the company, but you do have stakeholders in that sense too. So.
How do you balance the kind of weighing of wanting to share new results with the community so that other people can make progress based on those results, and your competitive spirit where you don't want to share your great results with other people? Is there what is the discussion when deciding whether to publish something or keep something confidential? What does that look like? How do you, what are the things that like go into making that decision for y'all?
That's to me, and I'd love to hear from other folks too. So it's a very, that's a hard decision. That's I try to do things, being more on the academic side, I tend to lean more towards open source. Then I have to go back and ask myself, is this providing a competitive advantage? If it's providing a competitive advantage, then we cannot necessarily share it. Workshops is a great example. And in my last job, we did because I was working on the other side of the fence, we did a great job pulling people together and identifying pre-competitive, what are the challenges? What are the use cases? Here's where we think people can work. And then people go off and work in their own areas at which they do develop competitive components to those answers. Personally, I love being collaborative. I love working with people. I love learning. It is hard though, and usually it's not going to be my decision. We have to work with the other organizations within the larger organization to say, hey, can we say this? Can we do this? Can we share this? And so it depends on our roadmaps.
Thank you. Paul, do you have any thoughts on that too?
Yeah, it's a very good question. I think, to echo what Tam was saying, I could see it being a big challenge as for a research team within a bigger company having to make those decisions. I think I'm very fortunate. Xanadu is a really great place because we act like an academic institution that is VC funded. We open source everything that we develop. We publish everything that we research. The only thing I can't think of really anything that's sort of locked in a cabinet somewhere that we don't show to anybody. And if there is anything that secret, usually we'll put a patent on it as well, but we'll still publish it eventually. It's great being the kind of that size. So that's one advantage I see with the startup. I mean, I guess we're not so small anymore, we're almost 100 people. So maybe small to medium sized startup is that we are a bit more agile. We're able to move a bit more quickly and to do those make those decisions to just open source things without a big fight or a big internal battle over that.
So yeah, we're getting questions. Megan, do you have anything to add to that? Or?
Not too much to add. I can definitely echo the difficulty of coming from a large industrial company where you keep things, to your business and to your team, and coming to a quantum computing realm where you publish your results and your discoveries and your findings. And having seen that in the machine learning world as well, and as well as the open source software, it's a bit of a battle, I think. So yeah, it's certainly a balance to be struck.
Thank you. Yeah, so the first, and anyone can, whoever feels like answering, can jump in for the audience questions. So the first question we have is, how far are we to move from developing new low-level quantum gate algorithms to higher level user-friendly algorithms?
Yeah, I could maybe take a stab at that. I think right now, if you go to implement some new quantum algorithm or new idea on the quantum computer, you need to use those low-level gate model abstractions. It's kind of hard to avoid it. Kind of the foundation to, okay, how's the quantum computer working? But I would think that as the quantum applications are developed and as we know more about like where that value really is for those applications, then that's where I think the higher level abstractions will come. So someone like me coming from, as being an operations researcher, I don't think about, gates on a quantum computer. I think about objective functions and my constraints and my variables, and that's how I typically set things up. So I think that I can see some of that's already started to come. There are already things where you can do mappings for optimization problems, for example, so people outside of quantum computing can, translate their problem to a form that the quantum computer understands. I can see that, as people figure out really good ways to do things, then that's where those higher level abstractions come.
Great. Thank you. Does anyone else have any input on that question?
This is Tammy. I'm going to echo. It's a great question, and there are tools being developed. They are different levels of sophistication. But one thing that I've observed, with computational chemistry and AI/ML is that I know a lot of the folks in the classical world and the computational chemistry side, and I look, and then I look on the quantum side and I go, well, there's just not a lot of overlap here. And I think one of the pediments, and this is an opportunity space, is developing tools that can achieve higher level languages that make it easier to use. So bottom line is, can you make it easier to use? And I want to applaud Penny Lane. They do have some pretty good documentation too. So, but yeah, documentation and tools to make it easier for people coming from more mainstream, so that we can drive adoption and get feedback to overall improve the system is a phenomenal path to undertake.
I have a question for people from the industry. I have a question. You talk about the interfacing with academia a little bit more, gets feedback in and out. So from the academia point of view, which is my has been my job for the last 30 years, I do not see how still industry may interface properly with academia, because this as you were discussing is somehow the secrecy of the industry world, combined with the fact that when we interface with agencies that come from the NSF, the DOE, the Department of Defense, and many others, the Air Force, they tend to funding of the work that the academician puts in. It's directed research to get something that's changed. Does industry have anything comparable to that? Because it seems to me that it's too much investment maybe for an academic point of view to put a graduate student to work on an area that can, for instance, that a student cannot publish or even not get funded by them. Do you know anything? Can you comment about what is the strategy for industry people with this kind of basic applications, as you call them, on machine learning, on a very innovative or new quantum technology that is no one knows exactly how it's going to develop? How can you do that interface industry with academia in a way that is more comparable to funding? I don't know if that question was established.
So the question was a little garbled. So it sounds like, I know you're probably not close to your microphone, but is the question, how does industry fund academia? Is that the question?
Right. How it's, when we consult with people away from academia, usually it is in exchange of some funding. So how does it work with industry in this very basic work you're doing, which is machine learning and quantum computing. Machine learning is a very new, technology from applied mathematics point of view, right? It's really numerical systems that you have to do inversions constantly and so on, and depends support for what exactly. So my question is, how does industry interface with academia on things that you may need to have a constant effect? I know that,
Sure. And I'm, again,
developing all this new idea and not sharing it with academia. That's something I don't you see it so well. For instance, NSF, people funded by NSF or DOE have much more freedom. So that's, I wonder how does how do you view the interaction?
right. That's a great question. And just a quick answer to that too is partnerships are key across the board in this ecosystem to driving the overall growth of quantum computing, period. It's not going to be one company or that. And so academia has a huge role, which is also technology development, workforce development, ecosystem. There's a I think UTSA, you have the Cyber Manufacturing Institute, for example. You also have, I think it's ARL, or is it AFRL? I think maybe AFRL South, where you have a node for research down there. The ways we work with industry, with academia, is direct collaboration. On the theory side, experimental side, we hire interns if you're interested, in a variety of fields. We're proposing looking at ways to work via federal awards, which will be a win-win per se. So yeah, there's a bunch of opportunity space. It's probably not going to, well, some of it could be a direct contract, could be a CRADA. But there are lots of ways that industry does work with academia, and we'll have to continue to do so to drive the overall growth.
What are the areas that you're higher?
We're over time for the session, so lots of good questions, but yeah, we're time constrained. So thank you everyone for participating. It was very interesting. Hopefully the audience got a lot out of it. I did. And with that, thank you.
Great, thank you very much.
Thanks for having us.
Thanks, guys.
Good afternoon. It's now my pleasure to present our afternoon speaker, who is David Dean, the Director of Quantum Science Center at Oak Ridge National Laboratory. He also serves as the principal investigator for the Quantum Science Center at DOE. The center incorporates research from across the integrated QIS innovation chain that includes fundamental science, R&D, device development, prototyping of new quantum devices and sensors, and a wide range of quantum computing and sensing applications in material science and the fundamental science of dark matter detection. Previous to this position, Dean was the Associate Laboratory Director for the Physical Sciences at RNL, and has also led the physics division in Washington, D.C. As a senior advisor for the Undersecretary of Science. Dean is a fellow with the American Physical Society, the Institute of Physics, London, and the American Association for the Advancement of Science. David, over to you.
Thank you very much. And I also want to thank all of you for allowing me to kind of switch my time around. We didn't realize until Wednesday this week that there was a huge conflict and I was supposed to be in two places at once. And even though I love quantum mechanics, it still doesn't work quite so well in the classical world. So thank you for the organizers helping us to make this happen. So I'm going to show my slides and start a presentation here. let's see. I think this is the one. We shall see. And hopefully everybody can see this. I'm hopeful. And let me go to full screen mode. So I actually am going to talk about the Quantum Science Center in pursuing the scientific grand challenges of the development of quantum information sciences. And I just listened to the panel discussion that folks had just now, and I believe a lot of points in this talk will mirror what you were talking about just a minute ago. And so let me start by relating to something that's classical in our classical world by thinking about Julian Linenfeld, who really kind of came up with transistor theory and wrote down what you should do to make a transistor in about 1926. And this was early, of course. Quantum mechanics had been developed in the early part of the 1900s, and this was an early development on the theory side. And it took about 20 years until Bell Labs made one single transistor sitting on the little piece of silicon there. And it was an first integrated circuit, basically. Bardeen, Shockley, and Bratton made that, got a Nobel Prize for it. And then Shockley and Fairchild and Robert Noyce got together and created the first IC, the first integrated circuit, which is sitting here through Fairchild IC. Robert Noyce went on to make to found Intel. And from that point, and starting maybe about 10 to 15 years later, you started to see the advent of actual computing and computer chips. The Intel 4004 was probably the first one commercially available, and it had 2,250 transistors in it. And of course, if you go to the late 1980s, early 1990s, computers like this one, one of the first Apple laptops was sitting around with 16 megahertz of frequencies on the chip, 200,000 transistors now. This is basically 20 years later, 200,000 transistors. It weighed a lot, 16 pounds, and it cost about $15,000 in today's money. And so I, as a graduate student, remember running around the country with one of these. It was very heavy as a late graduate student. I am very thankful for today's few pound instantiations. And of course, we have phones, iPhones, which run on 11.8 billion transistors. They have 6 cores sitting in them, 3 gigahertz frequencies, and neural engines so that they can recognize your face and your voice. It's just really, and your habits. And it's just really amazing how the technological growth has happened over the last 40 years. And it only cost $1,000 in today's money compared to this thing, which cost $15,000 back then in today's money. And so, you see Moore's law, you see all of those kinds of things in this graph, and it's really amazing to look at and to recognize the history there. And so if I just do about the same thing in quantum, what I see is in the sciences, it was an early idea, a curious idea, first developed by somebody like Richard Feynman, a Nobel laureate for his discoveries in QED, quantum electrodynamics. And Benioff was another early person who discovered it. Toffoli gates, people wrote down gates and how you could actually make a quantum computer do gate calculations. All of this was happening in the 1980s. It was all theory in the 90s. In 2000s, early 2000s, we saw the first proof of principle demonstrations and initial quantum computing type hardware, single atom traps, single superconducting transistor and superconducting loops and wires. And error correction and control theory were also developed for the chips and for the wires. And all of a sudden in 2010s, people began just 10 years ago to focus on the practicality and improving the quality and control of the hardware in order to do something interesting. And then circuit synthesis came along, and these guys that are sitting on the screen here, I should mention, Peter Shor was a factorization algorithm, Shor's algorithm, which was a quantum Fourier transform at its base. You have people from IBM and IonQ here on the screen, Jay Gambetta and Chris Monroe, Martinez from Google, Michelle Simmons from Australia. And all of these people were integral in creating the first generation of machines. And of course, they all had materials behind them. Charlie Marcus over in Europe and at Harvard making the types of materials you might need. And of course, things in the last 5 years have gone really fast into venture capital. And they've also gone really fast into going into the marketplace. So IonQ was just listed on the New York Stock Exchange, what, a couple of weeks ago. So really fast, really interesting times. And a couple of the chip designs that we have, two types of technology really. One of those types is the atom traps, and the other one is the superconducting qubits. And the federal government has been involved in quantum research for a long time. And the NQI Act in 2018, signed into law in December 2018, really gave the government impetus within the DOE in particular to get into this world to really help improve either algorithms, where we're very strong at the Department of Energy in classical systems, to improve those algorithms, or to improve the hardware, or improve the materials going into the hardware in conjunction with various companies. And so significant developments have gone on at IBM, Google, Honeywell. I think we just heard from Honeywell on the panel, IonQ, Cold Quanta, Rigetti, a whole number of other folks that I could list here. These are just representative. And so everybody here, or many of you, I know this is also a machine learning workshop, so it's kind of hard to get machine learning and quantum together, except in a couple of algorithms, and I won't talk about those too much. But what you want to do with the quantum computing is really to exploit key properties of quantum mechanics to compute. And there are two properties I'll just highlight out of several. One of those is this idea of quantum state superposition. In a classical computer, a classical chip where you have bits of information, the bit is either 1 or 0. It's either on or off. It's not on and off. In the quantum computing world, it is on and off at the same time, and this is called a superposition of states. Now, physically, what you're looking at here is an electron. An electron has something in it called spin. A spin in an electron can be either spin up or spin down. Spin 1/2 up or 1/2 down. But you don't know which spin it is. So when, in the absence of any magnetic fields or external forces, the electron is actually in both those states at the same time. And that's the projection of the spin onto this z-axis of the electron. And that is really the essence of why a qubit is actually described by two pieces of information rather than just one piece of information. And you can imagine if I get multiple qubits together, multiple electrons together, if you will, and they're all doing oscillations, then to describe that overall system requires 2 to the n, where n is the number of electrons, 2 to the n pieces of information to be able to describe in completeness the wave function of the system. And if you exploit that, it immediately tells you that if I have 30 perfect qubits with, spin 1/2 in each one, 30 perfectly entangled qubits, then that's 1 billion pieces of information. that I would have access to or that I could utilize to calculate. And a billion pieces of information takes me a billion bits in the classical world. So it's a really big difference. And that's the power that we're trying in quantum computing to get to with all the things that we're trying to do these days. The other piece of this is quantum state entanglement. Now, I've told you about superposition. All of the electrons have to talk to each other in order to get to this number here. And in quantum state entanglement, which goes over into actually communications, quantum communications, so quantum networking, what you need to do is just take two of these qubits and have them prepared in a state which is state up and down like this. Now, they can always be in either of these states, but they're state up and down. And if I then I can then pull these guys apart, they're still oscillating. I can pull them apart across the universe. And if I measure one and it's in state up, then I know that the other one is automatically in state down with instantaneously, I know that, which is called something like Bell's inequality. And it just kind of means that the information that you measure over here, you know about something about this system over here, even if it's across the universe, which is quite spectacular, actually, in terms of thinking about some of the deficiencies maybe of quantum mechanics. But we're going to exploit those two properties in what we do. And when we do that, we can start to look at what kinds of problems could be solved. And here I'm talking about physical problems that could be solved with a quantum computer. So, for example, in this picture, you see this BPQ region. And the BPQ region is bounded quantum polynomial region of this big phase space where I might be able to calculate things. And what that means is that there exist algorithms that are polynomial scaling with the number of terms or the number of dimensions within the algorithm space. And that polynomial scaling means that I can actually do some sort of computation on a limited piece of hardware. And so the types of problems that one might solve in the physical world, you talked about this a little bit in your on the panel in the previous discussion. Those types of problems are problems in chemistry, problems in materials, half-filled Hubbard models, quantum Fourier transforms that go to factorization, also field theories, quantum field theories, which go towards lattice QCD. Any type of Hamiltonian formulation of the quantum many-body problem should be representable on a quantum computer and should be calculable. You should be able to calculate properties of given classes of materials or chemical chemistries on these systems. Now, that's good. And for the Department of Energy, it really brings up the question, what aspects of classical algorithms remain as we transition to quantum algorithms? For example, Shor's algorithm, the factorization algorithm, is actually has a lot of classical part to it and a quantum part to it. So, figuring out in all of these algorithms, what's classical and what's quantum and how you put them together is one aspect of the problem. And then how and when will we make a discipline-specific difference? This is really important too, because if you're getting money from basic energy sciences in the DOE, in the Office of Science, they might want you to solve a particular type of chemistry problem. They don't care how you get to the solution. But if the quantum computers aren't up to solving that problem, that might not need to be funded. And so that from that point of view, we have a ways to go. And of course, all of the applications in chemistry and all the applications in materials ought to downfold into industry at some point. And so you have a pathway there that needs to be followed. So as I kind of mentioned, and has been alluded to, superconducting loops and trapped ions are the two technologies that have been commercialized, at least at some level at this point. IBM being sort of the moniker and Rigetti of the superconducting loops, and also Google, and in trapped ion space, IonQ and Honeywell being the other large players there. Of course, Xanadu is pursuing photonics. I didn't put photonics in this picture. This is actually out of a science article from a few years ago. Silicon quantum dots is people are pursuing that both at Princeton and also at the UNSW group out in Australia. We decided, the Quantum Science Center actually decided to look at topological qubits. And the reason we decided that is because of the strength here at Oak Ridge National Lab and also in our partners in the topological or in the quantum material space. And we also looked across the nation to see that there's not as much competition in the topological qubits as there is in the other areas. It's an open area, and it also has some physical advantages, which I'll talk about in just a few minutes. So there are other types of systems one could pursue as well. For example, diamond vacancies that's going on at Chicago. When the Office of Science began to jump into this area, and you know what, the government has funded research and development in quantum computing and quantum algorithms for a number of years, mainly through ARPA and NSF and IARPA and all these various places. But the DOE started to realize in about 2016 that they had strengths and capabilities that could be brought to bear on some of the materials aspects and the problems within quantum computing. And I think I haven't really mentioned, but one of the problems in quantum computing is just the scale up. How do you go from a few qubits to multiple qubits? And then the other problem, which I've implicitly discussed, is the noise within qubits. Each of these systems is noisy. It's either noisy or slow, one or the other. And the noisiness within the qubits means that they decohere quickly, and they decohere faster than you can actually do a substantial calculation on them. And so that's one of the things that we have to get around as we do the research to move forward. So within the Office of Science at the Department of Energy, there are these 6 programs listed. And OSCAR is the one, Advanced Scientific Computing Research, is the one that does a lot of algorithm development, computer science development. They have some of the world's largest computers. They're just about to make the exascale machine, the first worldwide, first exascale machine. All these kinds of things are going on through OSCAR space. BES deals with quantum systems and quantum materials and some computing and model making and measurement capabilities. And high energy physics, and this is called basic energy sciences, high energy physics deals with field theory, dark matter, and gravity, but they also do a lot of detection. And they like detectors. They like quantum sensors and want to develop those sensors to actually look at some of these very interesting phenomena that happen in the universe. Those 3 offices, in addition to the other offices, have fundamental science going on, some quantum computing, quantum communications, and quantum sensing going on. And so the department began to build up a program in about 2016, and they started funding at a low level in FY17, some projects. And by FY21 here, this last fiscal year, they're funding about $270 million worth of activity in quantum information science. And in the FY22 budget, they're expected to fund about $300 million worth of effort. So the field is still growing within the department. Now, the BASE program was started in the first 4 years, and the BASE program does some very interesting things. So I just have a couple of examples here from Advanced Scientific Computing Research. Quantum Scientific Computing Open Users Testbed, QS Scout, is at Sandia Labs, and Advanced Quantum Testbed is at LBL, or Berkeley Labs. And what they're doing here is just providing to the community of scientists the platforms, either the superconducting qubits or trapped ions. This is a Sandia trapped ion setup. They're actually providing to the academic and national lab partners the ability to come in and run experiments on these types of machines and try to understand how algorithms work on those machines while providing access, direct access to the hardware. So, you know, the IBM model is to go get your qubits on the cloud, which has been successful. This is more of a research model for go get your qubits at Sandia or Berkeley and make them do stuff for you. So that's one aspect of the base program. And another aspect is this idea, and I pulled this picture from Oak Ridge, is the idea of pulling or taking materials and doing material science research. And in this specific instance, Stephen is actually embedding defects in a material and trying to control where those defects land within the material. That's one of the projects that BES is working toward. You can imagine if you could control defect placement in a material, you can also control how that material could be used as a computing device. And you can also control how growth of materials for superconducting computers or for topological type computers would be used. So these base programs led to an explosion of research within the Office of Science. And at the same time, the NQI Acts came along and said that they would, that act said the DOE would set up 5 centers, each at $25 million a year. So $125 million a year worth of new effort in quantum information science. And this is a 2 sides of a brochure that we've put together as a team. This is the National Quantum Information Science Research Centers, and they are led by 5 different national laboratories and include all these members in their activities. And you see a whole lot of different types of universities, some companies, and then the national laboratories which are involved. And so here are the 5 centers more explicitly, one at Brookhaven, one at Argonne, one at Lawrence Berkeley, and Quantum Science Center at Oak Ridge, and then the Fermi National Laboratory centers, the SQMS at the bottom of the page here. The centers have different chief foci, I would say, different places where they're really putting effort. For example, QNext is working on transmutation of information, how to move it around in systems. Brookhaven is working on making the materials better for superconducting qubits. The SQMS is making cavities to contain qubits. And then QSA is working on the algorithms and the stack, and also making superconducting efforts and trapped ion efforts better. So I'll talk about what the Quantum Science Center is up to during the remainder of the talk. Oh, I'll give one highlight. I think this is a beautiful highlight. This comes from the QSA team at Harvard, MIT, and Berkeley. And what they did is they took Rydberg states in 256 atoms and made a programmable analog quantum simulator out of that, where they could set the machine up, actually make the machine do something, do some sort of evolution of the machine underneath fields, or underneath, right here, underneath some sort of operator which does the evolution, and then do controlled readout to see what the answer is. And so this is really just a beautiful demonstration of where we are in analog computing space, where you can get your Rydberg atoms or your trapped ions to do calculations for you. Now, it's not the same as the gate-based approaches. but it is a way to do stuff to investigate materials properties or other properties within the system. In fact, in the paper here by Baldi et al., they talk about anions within this particular system that they are trying to mimic and trying to understand. Now, the Quantum Science Center is led by Oak Ridge National Laboratory and is funded by the Office of Science. So I'll talk about the QSC for a while. And what we saw as we were developing the proposal and the team, you know, all of these centers have as a goal to overcome key roadblocks in quantum state resilience, really to make the coherence of the states last long, a long time compared to the calculational time needed to do something interesting, to the controllability and ultimately scalability of quantum technologies. Right now, we're not really scaling up to the thousands and thousands of qubits one might need in order to do error correction and to have capability to calculate things. Well, let me just give an example of that. If you have 30 perfect qubits, you'll remember I said you'd have 1 billion pieces of information that you would need there. But to get to 30 perfect qubits, you might need 3,000 physical qubits. So to get to 100 qubits, you might need 10,000, you know, physical qubits. So I think that's the scale up problem, how to go from our standard computers today of 60 to 100 qubits to get up into this world and range of 10,000 to 100,000 qubits. That's a big problem. How to overcome the noise within the systems as you do that, and to keep everything coherent as you do that, keep all of the qubits coherently mixed. So that's the challenge. And our approach to this in material science is to address the fragility of quantum states through the design of new topological materials for QIS. And so why topology? I think I'll talk about that in a few minutes in more detail, but the short answer is that topology can be used to protect quantum information. And it protects the quantum information from external noise within the system, which means that the states, the qubits, can actually live longer and be used to calculate things within the system. We also do computational science in the sense of developing quantum algorithms and software for computation and sensing with current and future QIS hardware. The algorithms are fault tolerant or useful for today's machine. We're actually targeting both. And as you make those algorithms, they're focused on trying to solve problems of relevance to DOE missions in material science, chemistry, and also a little bit in nuclear physics. And so that's sort of where our computational efforts are going. And then in sensors, we design new quantum devices and sensors to detect dark matter and topological quasiparticles. It turns out that the excitation energies of these topological materials and systems, or topological quasiparticles in the systems, is about 1 millielectron volts. And at 1 millielectron volt, also there's this thing called dark matter, light dark matter, that hasn't been detected yet, but it's at the same energy scale. So if you design qubits to detect and techniques to detect excitations over here in the material space, there's a lot of synergy there with what you need to do in the dark matter space. So that's a very nice scientific synergy that we see. The outcomes of the center will be accelerated quantum information processing, prediction of new physical and chemical behaviors, and then new quantum sensing capabilities to explore the previously unmeasurable. And the team is given here. It's a broad group of people, about 100 people, and these are the leaders of that team, about 100 researchers across 16 institutions. Travis Humble is the deputy director. Joel Moore is our chief scientist. Aaron Chow leads the devices and detectors thrust, and he's from Fermilab. Michael McGuire, hopefully I can hang up and, yeah, there. Michael McGuire actually is the thrust lead for our materials thrust. He's from Oak Ridge, and Andrew Schornborger from Los Alamos leads the algorithms thrust. We also have a pretty substantial effort going on in workforce development, and Sasha Boltaseva from Purdue leads that effort. I think we've had a really great first year of operation, 61 research journal articles, creation of 8 intellectual pieces of property, including a couple of patents that have been filed for, and we're also have 40 postdocs within the center and 12 students. The list of places you see here, there are 4 national laboratories, 9 university partners, and 3 industrial partners, including Microsoft is one of our major partners, IBM, and Colt Quanta. So the QSC integrates capabilities to overcome these roadblocks. Now the capabilities at the DOE laboratory system are very broad. We've got neutron sources, and we utilize those neutron sources extensively there at Oak Ridge, both the SNS and the HIFER. We have nanophase material centers where you can do materials developments, both at Oak Ridge and Los Alamos. The Mag Lab at Los Alamos, which is an NSF-funded activity, actually has very high magnetic fields that we can access to characterize some of our materials. Of course, computational capabilities at the various laboratories that we access, and light sources as we go through this. So that underlying capability suite of national user facilities at the national laboratories really enables this kind of research in the materials aspect of what we're up to. So let me go through the topology for a little bit and try to wrap it up. So our first thrust, the topology of quantum materials, really offers robustness against noise. Now, if you're in a topological phase of matter, you know, the quantum information is really non-locally encoded in underlying microscopic constituents so that it's protected against local perturbations. I think if I have my coffee cup here, here's my coffee cup, if you see it there, you notice that it has a hole here. And from a topological point of view, I can take this coffee cup and manipulate it. Now, not this coffee cup, but from topological point of view, I could manipulate it into a donut, and it would be the same topological object because of that hole right there. And so, and without tearing anything or without disturbing the system, except for small incremental movements of the system along the path to a donut. It's getting late here in Tennessee. I'm starting to get a little hungry. In the quantum mechanical system, it's a very similar idea. Of course, it's quantum mechanical. So what you have is you have a two-dimensional material, and within that material, you can drive various points within the material to make it so that electrons that are in the material can come together and create these quasi-particles. Electrons are electrons in holes. And those quasi-particles are actually like taking a qubit of information and transforming it across 2 or 3 physical particles. And because of the topology that you set up when you do that kind of thing, those particles are immune to external noise, thermal fluctuations, defects within the system. And that's what you want in order to compute. Then you take those 2 quasi-particles and you actually move them together or move them around each other in a particular fashion. This is all within 2D. And when you do that, 2 dimensions, and when you do that, you can actually compute things and set up a gate computations. So here, the challenges are the design of these two-dimensional spin-liquid materials and spin-liquid materials with the topological states, and also the unambiguous experimental evidence of topological states. It's hard to find these experimentally. It's hard to define where they are in the materials. And then the control of the interaction between the states, which I just talked about with the states roaming around each other. And so I think I'll skip some of this. I'll just mention that long ago, one actually could do calculations, very simple calculations, to show in a high magnetic field how the electrons would behave. This is a density plot in a high magnetic field of how the electrons behave within a material. And then in the late 2000s, late 2000, 2007 to about 2012, people started to understand that if you put type 2 superconductor here with 2 degrees of freedom, did a little bit of placing of vacancies in particular places, you could actually get the field that's driving this behavior over here in the density plot to kind of collect in different areas, and that's where the quasi-particles, the anyons, would actually exist. And so by introducing what effectively in the magnetic potential, electromagnetic potential, effectively is a delta function into the materials, you can actually get this to happen. Now, it's easy to write down, it's easy to do calculations with, it's not so easy to prove experimentally that you actually have these states. That's what we're up to. If you have the states, if you can find them in the materials, then you can actually do calculations by braiding the states. Here's a little cartoon picture of what that looks like. Braiding means that you wrap these states around each other in a particular way. This is time going this way. And when you do that, you can actually calculate. And so I think that's what we're up to in the center, trying to do that, coming up with the algorithms that allow you to do that, and the experimental capability to do that as well. So I think I'll just show one example here of where we are in the materials effort. What we're doing here is making the topological materials design. Here you see some ARPES pictures of one of the materials we're trying to make. It's actually some of this thorium, chromium, silicon type material, and doing measurements of that material within an ARPES system. Bismuth selenium is another type of material that we're working towards as well. We're also working towards some of the uranium and F5 type materials as well. QSC is also developing algorithms and simulations relevant to the DOE mission. And some of these algorithms are fault tolerant. Some of these algorithms are not. They're made for NISQ machines today with some fault tolerance built in actually. And the idea there is to move toward algorithms that can handle materials and that can understand, or that can be used to describe materials. And using those algorithms to describe the materials would actually feed back into our materials thrust and create a co-design loop. We're actively pursuing that kind of thing today. So one of the algorithms that people are using or trying to investigate is, how do you take a huge Hilbert space and get it to a smaller Hilbert space where you could actually compute today, still maintaining the physics of whatever you're trying to do in that space. Here you have a two-dimensional lattice of atoms that you're working on, getting into a smaller Hilbert space where you could do computations on a NISQ device and seeing whether those computations really enable you to describe the physics that would go on within the material. That's one of the types of algorithms we're developing within the center. Another thing we're doing in the center, and this is in collaboration with PNNL and Oak Ridge and Microsoft, is developing languages or putting together languages with, for example, QCore, higher level languages, OpenChasm, I think is one of them, QSharp, putting all that stuff together into packages so that there's a higher level language that people can utilize in order to drive quantum computing, and also in order to do the simulations you'd like to do to understand how your quantum computer is going to act given a particular algorithm. And so that's also something we're working on as a center within the algorithms thrust. And we're also developing these MEV, milli-electron volt quantum sensing efforts. We're doing that for topological states, but I thought it would be kind of fun to highlight at the end of Friday here after a long week, to kind of highlight some cool physics that we're also trying to work on and also working toward. So it turns out that you have this, let me see this diagram here. You have this interesting problem within physics, not really physics and cosmology, but astrophysics, where if you look at a galaxy and you look at how the rotational speeds go in a galaxy, if the only matter within that galaxy were light matter, you'd have this nice curve here, this little red curve. And so the speed of this outermost particles would be very slow compared to the speed of something right here in the middle. And of course, at the very, very center, the speed would be 0. That's really cool, that's nice, but what you see experimentally, observationally, is a flat line. And what that means is that there's matter that you can't see that's actually keeping all these particles from slowing down as you get further and further away from the center of the galaxy. And so the question is, what's that stuff? And it's called dark matter, but it's not been seen experimentally. Now it might exist at the GeV scale. A GeV is equivalent to the mass of a proton. It might exist at the TeV scale. That's equivalent to supersymmetry, what's going on at the CERN collider in Europe. Or it might be at the EV or milli-electron volt scale. That's wave dark matter, which should be detectable, or very, very heavy dark matter. And we're actually doing squeezed optomechanics to look at the very heaviest regions. And we're developing sensors for these milli-electron volt regions as well. And so just to kind of close the loop there, one of the things that has to be developed when you think about particularly detectors of these qubit sensor squeezed optical mechanical detectors is that you have to have a whole series of them, a whole bunch of them in order to see any effect. And that means that you have to go back to engineering and develop the right kind of engineering boards to actually multiplex all the qubits together. And so this, and of course, if you want to do scale up of qubit technologies, you might want to do all of this on a chip, which means that going to cryoelectronics actually becomes important. And so Fermilab is one of the places within the lab system that can do that kind of stuff, the cryoelectronics. So we're developing cryoelectronics for these multiplexed type qubit systems and all for arrays of qubit sensors, and also for some of our activities within the quantum computing sector as well. Now, I thought I would end by talking a little bit about the innovation chain. It turns out within the call for proposals that we, all centers, were supposed to set up an idea of how you move across the innovation chain. It actually really is a way to organize what one does within these centers. You know, fundamental science, which is a lot about what I talked about, making devices, making prototypes, applications, and then systems. And, you know, the flow here, while it's not perfect in any of the centers probably, the flow here goes from the fundamental science to tech transfer. One of the things the laboratories have to do, it's part of the mission of the national labs, is to do tech transfer. So a lot of our efforts are actually have a collaborative research aspect of them with industry and collaborations with industry. A lot of our efforts in the research side are just internal to the center. So here's an example. And so, you think about fundamental science here. The guys have done growth, MBE, molecular beam epitaxy type growth of a two-dimensional thin film. superconducting material, which is thought to be a good material for holding these quasi-particle states. They're doing ARPES measurements. ARPES is angle resolved photoemission spectroscopy measurements on these systems to demonstrate that, yeah, indeed, they are pretty good candidates for having topological states in them or edge states. You can then take those materials and stick them into a device that's being developed at Purdue, where the materials would actually live in these little gray boxes. And if you do that, then you have a hope of making the materials, making the device so that you could study whether you can get the anyons to talk to each other. Now, there will be transport measurements, and this is a prototypical transport measurement, in order to look at current and do spin polarization within the devices, within, for example, this kind of device. And so that's also something that's going on as we move forward. And you might think that theory should not be an application, but in this case, the theorists, Jason Alasia at Caltech and Gabor Al-Aziz here at Oak Ridge, have developed a way to do basically anion interferometry to see how the anyons can talk to each other as they move around some of these device areas. And if they can talk to each other, and if you can measure the scattering, how the scattering would go if they're interacting, that would tell you that, yes, indeed, you have an anyon, and maybe you can start to think about how to manipulate it. So all of these things together are part of the innovation chain. And I admit on this one, I could have kind of done things a little differently, but this is the way we think about the center in terms of innovation. And Microsoft is a transition partner for the topologically encoded efforts here. One more is the innovation chain around quantum simulation platforms. We're developing a cryo-cooled ion trap at Oak Ridge. We have the ion trap. We're developing the electronics at Fermilab to make it cryo-cooled. I talked a little bit about that in the context of arrays of qubits for detection earlier. But coupling those two will enable us to demonstrate quantum algorithms for QCD, scattering algorithms for within quantum chromodynamics. And we can verify that those algorithms are actually working through validated demonstrations working with PNNL and Microsoft. And so this is, again, another demonstration of the innovation chain loop that we're going through as a center. So I think I can stop there, and I can just entertain questions. And I hope I've given you a flavor of how these centers work, what they're up to, and how this center in particular works. I do have AI slides from David Womble. I'm sort of a stand-in for David Womble, actually. He couldn't be here. But at the same time, I thought it would be just great to talk a little bit about what we're up to in the QSC. And I appreciate your time and attention. So thank you. And now I'll try to get out of sharing. And I hope I'm not the only one here. Is there a leader to this? Anybody? I guess you could put questions in the chat, or I could stand here.
Yeah, we're here. Can you hear us? David?
So I do see the whole Majorana's pullback had me thinking we were reconsidering, but I'm glad research continues. Yeah, there has been a little bit of pullback. And I believe that's because of a paper that came out in 2018 from Kouwenhoven and Company in Delft. Actually, the research is much broader than that particular paper. And so I would say that the effort there the effort there continues, really does continue across the board. I think what that pullback has taught all of us, is that you really have to be careful. These systems are fragile. They're non-trivial to create in the lab, and unambiguous demonstration that you have anyons within the system is what's important. And so those are some things that we have to worry about. Where do I see quantum AI going? I think AI, so QSC does have a little bit of AI work going on. It's really machine learning work going on, but it's in the classical context. It's in the context of helping us identify how to make the devices that we're going to make better. Now, in terms of quantum AI, the QSC has no effort there going on. There is some effort like that going on within Oak Ridge National Laboratory. And from what I can tell, what we are seeing is that you really need the ability to put into the quantum AI system data, and that's hard. And so I think that's where the research is, and I think that's what's going to keep people up at night for a few years. And once you figure that out, how to get data into a quantum AI type of calculation, I think you could do stuff. So that's what I know there. And I don't see any other questions. Oh, here's another one. As a quantum computer may speed up calculations, an AI classical may be slow as a dinosaur to process outputs. That's kind of what I just said. That's good. The combination may be highly inefficient. For what class of problems is that a combination expected to be efficient? I don't know the answer to that. I think that's where the research is. What identifying those problems will be the research of the next few years. All right.
I have a question. Can you hear me?
I can hear you.
Okay. I'm curious what you think about China's recent 65 qubit quantum supremacy experiment. I think the United States government should be doing something to push that technology now that they've surpassed the goal in industry, things they might say.
So this was the Chinese 65 qubit machine, right? Did I get that right? You broke up on my side.
Yeah,
so is that So I'll pontificate because I think I understood what you were asking, but I'm not sure. The qubits, first off, we don't know a lot about that machine in the US. We hear about it. I think we hear, that it's a good machine, but we don't know much more about it. So, and the technology, if I recall, is it's either superconducting or it's photonics. Now, photonics is being pursued in the US by some groups, so that's a good thing.
It's almost like in both. You have quantum supremacy in both modalities.
Well, I can't understand you because you're breaking up in the translation. But whatever it is, I think you could be. I think the US is doing stuff there. It might not be at that same scale. So I'm sorry, I can't really understand what you're saying on the other side. Frustration. So I appreciate your time. I'm going to have to get off and go to another meeting. And I really thank again the organizers for enabling me to come on sort of at a different time than I was supposed to come on. And thank you very much. We'll talk to you later. Bye-bye.
Now I have our closing address. I'd like to introduce Dr. Bernard Harulananda. Dr. Rule, as we affectionately know him at UTSA, is the Vice President for Research, Economic Development, and Knowledge Enterprise at UTSA. In 2018, he fostered the creation of UTSA's National Security Collaboration Center, which you might have heard about. He's a world-class immunologist and serves as the director of the South Texas Center for Emerging Infectious Diseases, as well as the scientific director of the Vaccine Development Center of San Antonio. Dr. Rule received a Fulbright International Education Administrator Award and is a fellow of the American Association for the Advancement of Science, the American Academy of Microbiology, and was inducted to the National Academy of Inventors. Lastly, and closest to my heart, he served as the founding executive director for the Open Cloud Institute. I give you Dr. Rule.
Thank you, Jeff. And thank you, everybody, for staying until the very end of this exciting two-day symposium focused on AI and quantum. On behalf of UTSA and one of our newest research center, the Matrix AI Consortium for Wellbeing, we appreciate your attendance during what we hope is the tail end of this pandemic. For those who attended in person, we thank you for flying, driving, and coming to Maryland to connect in person. For those who joined us virtually, we also thank you for your willingness to join despite the Zoom fatigue. This symposium is a confirmation of our commitment to transdisciplinary research in artificial intelligence and quantum computing. UTSA has invested in the talent and the resources required and is actively contributing to scholarly excellence as it impacts every industry in some form or another. And importantly, it complements our existing research portfolio in cyber and data science, for which we are known for. I'd like to personally thank Dr. Dirisha Kutupudi, the founding director of Matrix AI for Human Wellbeing, and for the genesis of the idea to create this exciting event, along with our symposium partners, Big Bear AI. A special shout out to Dr. Reggie Brothers and Mr. Eric Conway for Big BI's partnership for this engagement. I also like to share my deep appreciation to Missy Dreamport for sharing your resources and your facilities for this event. We are proud to support the creation of this forum for engagement with fellow researchers worldwide in building a strong and collaborative research community. This event demonstrates a strong collaborative research community underpinned by an excellent academic framework that has the potential to tackle global challenges. I know I speak for UTSA and all of the organizations engaged throughout this event when I say we hope to engage the global community to further understand how AI and quantum can address social and health challenges and provide ways in which they can support and advance our collective research efforts. In less than a year, UTSA will open a brand new building to house the School of Data Science in downtown San Antonio, including the National Security Collaboration Center, the Cybersecurity Manufacturing Innovation Institute, the Open Cloud Institute, and the Matrix AI Consortium, and other centers that are focused at cyber at UTSA. This is a highly transdisciplinary building, and it speaks to some of the things that we heard in the last 2 days. I personally would like to invite all of you to San Antonio to see this brand new building that's coming up next year, and for future collaborations, and to also further learn from our research centers at UTSA. With that, I'd like to close the symposium and thank all of you for your participation. Stay safe.